All right. I'll let other folks trickle in over the next minute or two, but good morning, everybody. Welcome to the 27th Annual CESM Workshop, joint session between Chemistry Climate and Whole Atmosphere Working Groups. My name is Nick Davis. I'm one of the co-chairs of the Whole Atmosphere Working Group. So today we'll have 4 sessions, 3 with presentations, and then a final wrap-up discussion. So our first session is going to be focused on musica and developments and uses of it. The second is going to be focused on model development. Third will be focused on science and model evaluation. And like I said, we will also have a future plans and discussion at the end. So the format is going to be 10-minute talks. We'll run the talks together in each little mini session. And then we'll have a combined Q&A and discussion at the end where you can ask speakers questions or have a discussion either on a specific talk or even on the main thrust of the session. Just want to remind everyone of the meeting code of conduct and to be constructive and kind when asking questions. And for our speakers, please be sure to end your talk at the 10-minute mark so that we can stay on schedule. As you can tell, our schedule is quite tight because we didn't want to have a poster session. So we would really appreciate it if you keep on schedule. So that's it for our introduction. I can turn it over to our first session chair.
Okay, thanks, Nick. Okay, I will start sharing the first session, and we'll be starting right at 8:35. So I guess we could start a couple minutes early. That gives us a couple minutes extra. Yeah, so our first session is mostly all on musica version 0 developments and overviews. And the first speaker is Louisa Emmons. Louisa, do you want to start sharing? And I think we'll just start right away. I assume that everybody is already in the session who wanted to join this. Okay, go ahead.
Great, thank you. Yeah, so I'll just give a little update on activities related to musica, and apologies to those of you who have seen this before, probably many times, but just to start out, our vision for musica is to really develop a model independent framework that will really facilitate swapping different chemical schemes and photolysis schemes and aerosol schemes coupled to an Earth system model, and for studies of the troposphere through the thermosphere. And we're doing this development in coordination with SEMA. So a lot of the activity that we hope will really lead to musica is still in development and design, but we have some configurations of CESM that we're calling musica, and are getting started on some of our goals for this infrastructure. So if you want more information, we have a website in the ACOM website, and a vision paper was published in BAMS a couple of years ago. So our goals for musica are really to develop this collaboratively with the community. And to do that, we have a few ways the community can be involved at the moment. So we have some released model configurations that I'll tell you more about in a minute. We've also run musica version 0 and are providing the output to the community. So you can just use some existing runs. And we'd also like to encourage you to participate in development. And we've established these different working groups to address different topics related to musica and improving the model representation of these. Web page again. So what we're calling musica version 0 is really a configuration of CAM-CHEM or WACM in CESM using the spectral element dynamical core with the regional refinement variable resolution grid. So one of the grids that we have available in CESM 2.2 is this grid of 14 kilometers over the contiguous US, then gradually increasing to 100-kilometer resolution over most of the globe. So this is really a nice capability for doing regional scale modeling, but still having the global model capabilities and connections to the other Earth system components. There are also a lot of tools, some tools available so you can create your own variable mesh, and I'll go into that in a minute as well. So the simulation that we've run and have provided output for is using this CONUS grid, and it's available on the NCAR GDEX, used to be called the DASH repository, but it's available for anyone to download. And we've currently run 2012 and 2013, and if you'd like additional years, we're happy to help do that, and you're welcome to get in touch with us. And there are additional details on the Musica wiki about the simulation, exactly the emissions and everything, and what's in the output. And if you have any questions, feel free to contact us. So several people have been developing their own grids and doing a lot of different studies. This is one example. Sergio Ibarra, who's now at NOAA GML, has used this grid over South America that was developed by Patrick Callahan for comparing to WRF, essentially looking more at the meteorology. And Sergio has now added chemistry, or run this resolution in CamChem. And so we have full chemistry simulations for this grid. Starting out, he's just using the half-degree version of this grid, NE30/2, but plans to look at the finer resolution and really to look at the impact of biomass burning on air quality at these different resolutions. Another grid that has been developed is Dusong Zhou has created this grid over East Asia that goes down to 7 kilometers over the Korean Peninsula with 4 levels of refinement gradually reaching that, and has been looking at how these different resolutions differently simulate ozone and gas phase species, and through comparison with the Chorus AQ aircraft observations as well as surface observations. And so the black lines here is the observations, the black boxes are the aircraft observations, and the 4 colors are the model resolutions at different resolutions, and show that you can get rather different answers for at these different resolutions. And while some of the coarser resolutions sometimes look better, that's probably not for the right reason. So there's a lot to investigate there to really understand the impacts of changing resolution. So we're trying to put together a library of all the grids that people have developed and that are available. And not all of these have been tested with chemistry, but or have some, like this Arctic grid, have been used for CAM studies, but we think could certainly be used for chemistry. There's a grid for Europe, East Asia, Africa, Australia. And so we've started this page on our wiki site that gives details of what the resolution is called, where you can get it, who to contact, whether it's been published. And so if you're working on making a grid, we'd love to have you share it with us, and we can include it on the wiki page. And if you're interested in using any of these grids, please have a look and contact the people mentioned for more information. So yet another sort of grid we're working towards using is the MPAS grid, which is a hexagonal mesh that can go down to even finer resolutions than we can run with the spectral element, because it's a non-hydrostatic dynamical core, and so we can go down to resolutions less than 1 kilometer. And so we're currently testing that, and Mary Barth and Francis Bitt have a plan over the next year to do some extensive tests with this grid, which is 60 kilometers for most of the globe and 3 kilometers centered over Southeast Asia, to look at the Asian summer monsoon and convection and transport in the UTLS. So it has 840,000 grids, and they're going to try with the 32 level version, but also higher levels and the full chemistry scheme. One other topic we've been working on is a model evaluation tool called Melodies Monet. And this is a Python-based framework that will facilitate comparing model output with atmospheric chemistry observations. And Monet is a package that already exists that was designed for comparing WRF with surface air quality observations. And we're extending it to include comparisons to aircraft data and satellite observations. And so this picture on the left is sort of the structure of this whole framework. And there's a YAML configuration file, which is a text file, the specific format, like kind of like an XML file, that defines which models you want and which observations you want to compare and what plots you want to make. And then it runs a tool to read in the model, and it separately reads in the observations and put them into standard format, and then does the pairing and produces a lot of plots and statistics. So it's Python based with standard libraries, and we have a lot of Python notebook examples. And then it spits out plots like this, which is the model results with the AirNow observations overlaid them, and something like a box plot of the statistics of the observations in the model, and lots of other plots. And we are definitely also would love to have community assistance in further developing this and reading different models and observations and producing output. And so then finally, over the past year, we've ran a Musica tutorial series, and this is the webpage for it. And so we had a session about each month and showing how to look at Musica output and running the model. And all the videos and slides from each session is available online. And we encourage you to have a look at those if you'd like to get started with any of this, and provide us feedback if you'd like additional sessions. And we also have a Musica mailing list, and which you can sign up on the Musica webpage if you'd like more information. And I'll stop there since I started 2 minutes early. Let's go on.
Thanks, Lisa. As Nick has explained, we have questions at the end of the session, so you can put them in the chat if you have direct question, and Luisa can answer them as well. And while I'm introducing Nori, please start sharing your screen. The next speaker is Nori Maziska. And she's visiting ENCA right now. She will talk about evaluation of models simulated ozone and its precursors in Musica version 0 against in situ airborne measurements over the continental US. Please go ahead, Nori. Thank you.
Thank you so much, Simone and Luisa. Good morning, everyone. Like Simone mentioned, my name is Nori Beth Mariskal, and I'm a grad student visitor here at NCAR with the ASP GVP program hosted by Dr. Emmons. So today I will be presenting the status of the work that I've been doing evaluating model simulated ozone and its precursors in Musica version 0 against in situ and airborne measurements with a focus on Colorado and Michigan. The main objectives of this project are to understand the causes of ozone production in areas of non-attainment and their impact on ambient air quality using high resolution chemistry climate modeling. Additionally, this project also aims to investigate the sensitivity of model horizontal grid resolutions to atmospheric composition and chemistry. As Luisa mentioned earlier, the multi-scale infrastructure for chemistry and aerosols version 0, or simply Musica version Zero is a configuration of the ChemChem Global Chemistry Climate Model using spectral element dicore, which is that unstructured grid mesh based on a cube sphere, allowing for regional refinement. The model has a comprehensive representation of stratospheric and tropospheric chemistry, and I employed Musica version 0 to look at summertime ozone and its precursors using the anthropogenic emissions from CAMs, biomass burning emissions from FIN and QFED, and then vegetation emissions using the Megan algorithms in the community land model version 5. I initially ran the model from May to August of 2014 using that default resolution of approximately 14 kilometers over the contiguous United States and 1 degree for the rest of the globe. The model output from this run was then sampled along the flight tracks of Frappe and Discover AQ Colorado, as well as evaluated with various surface measurements from both campaigns. The Frappe and Discover AQ Colorado campaigns were held jointly by NCAR and NASA respectively in the summer of 2014 with the goals of identifying main drivers of summertime ozone in the Northern Front Range metropolitan area and understanding sources, transport, chemical transformations of air pollutants, and how they relate to satellite observations. Frappe included the NSF NCAR C-130 aircraft and ground site measurements, and then Discover AQ included the P3 and B200 aircrafts, as well as ground site and remote sensing measurements. And then on the right of this figure, you can see the flight tracks of each aircraft. So the early Musica version 0 model simulations for the summer of 2014 demonstrated that biogenic VOCs, isoprene and monoterpene specifically, were being overestimated in the model compared to aircraft observations from Frappe, with normalized mean biases of 263 and 46% respectively averaged, across all the altitudes here on the figure to the left. Isoprene and monoterpene emissions in the Northern Front Range metro area make up 13 and 21% of total Colorado emissions, without taking into consideration the emissions from the mountain region to the left of the NFRMA region in Colorado. In response to this, we decided to constrain the biogenic VOCs, isoprene and monoterpene, by reducing emissions in Musica version 0 by 75%, 50%, and 25% for the summer of 2014 in order to quantify their impact on ozone production. The figures to the right of the slide show that reduction for isoprene and monoterpene, where figure A shows 100%, B is 75%, C is 50%, and D is 25% of biogenics present in the model. So once the sensitivity simulations were ran, I analyzed the differences of surface ozone concentrations between the control simulation and the sensitivity simulations, with that focus on Colorado. Based on these plots, it can be seen that in comparison to the 100% of biogenics present, the further reduction of biogenic VOCs in the model leads to nonlinear changes averaged over Colorado, with maximum changes of almost 3 parts per billion. I mean, the reason that I'm looking at this is because of the Rocky Mountains and the focus on the isoprene monoterpene emissions. So in order to quantify the impact of biogenic VOCs on ozone production, I began by evaluating the vertical profiles of various sensitivity simulations against the Frappe C-130 aircraft measurement, and found that isoprene and ozone agreed best with observations when there was 50% presence of biogenic VOCs, monoterpenes when there was a 75% presence, and formaldehyde when there was a 25% presence. Overall, isoprene, formaldehyde, and ozone concentrations showed better agreement with Frappe when presenting that reduction of biogenic emissions, while monoterpenes remain underrepresented, particularly in the higher altitudes here. In addition to evaluating the model against aircraft observations, I also was looking at the VOC measurements from the UC Irvine whole air sampler data sets available on the NASA and campaign website, and divided the data by region. In the red, we have designated that as the Rocky Mountain area. The blue square is the foothills. So it's that region that is not quite the mountains, but not quite the urban area. There's also the urbanized area in the green, and then the yellow box represents the oil and gas as well as agriculture areas. So for this particular data set, I plotted here each simulation per region with the plot with the gray bars on the top left corner, representing the total data points available per region. I found that isoprene, which is the top figure, agreed best with observations when there was typically between 25 to 50% of biogenics present in the model, when looking both at the mean and median biases for each region. For monoterpenes, which is the bottom figure, in terms of the mean bias, the model agreed best when there was a 75% biogenic VOCs present in the model, with differences up to approximately 18 parts per trillion. And for median biases, it was between 25 and 50%, with changes up to 14 parts per trillion. Although no concrete conclusions can be made at this time about which sensitivity simulation agrees best with observations, it can be noted that the biases for isoprene and monoterpenes are reduced when the biogenic emissions in the model are reduced. So additionally, in order to look at the sensitivity of ozone to model grid resolution, I am refining a grid over Michigan at about 7 kilometers. I plan to run Musica version 0 simulations using this refined grid to look at particularly the ozone atmospheric chemistry over Michigan and compared to the MOOSE campaign measurements. So MOOSE, or the Michigan Ontario Ozone Source Experiment, is led by the Michigan Department of Environment, Great Lakes and Energy, with various participants from universities to federal agencies and Environment Climate Change Canada. This campaign seeks to define potential attainment strategies in Southeast Michigan and better understand what contributes to the ozone exceedances in this area. So MOOSE Phase 1 began last year from May 24th to June 30th of 2021, and MOOSE Phase 2 is continuing on this summer. So, and the images here just kind of show the monitoring sites where some of the sensors have been located. So in summary, the preliminary findings of the Musica version 0 simulation output evaluated against the FRAPE C130 flight track dataset determined that isoprene and monoterpenes were being overestimated in the model. So with this being said, we decided to reduce the biogenic emissions in Musica by 25, 50, and 75%. The initial analyses with the aircraft and stationary data sets from FRAPE and Discover AQ were also conducted. And then although no conclusion can be made at this time, the initial model evaluation with aircraft and whole air sampler measurements does point to that the reduction in biogenics in the model will help reduce the discrepancies between the model and the observations. Further analysis is needed to better evaluate the model and determine optimal biogenic VOC content. One suggestion has been to potentially regrid the actual vegetation maps used in the model. So that's something that we're currently looking at. And then I also plan to continue the Michigan grid this summer with NCAR. So I'm excited about that. And then I'd just like to acknowledge NCAR, the National Science Foundation, and NASA's Michigan Space Grant Consortium for supporting this project. I'd also like to acknowledge the Cheyenne Supercomputing Support team. I would also like to thank FRAPE and Discover AQ Colorado Science teams for their campaign data sets, which have been really helpful. Yeah, that's all. Thank you.
Thank you very much. Very nice talk. And again, please put your questions in the chat for now and keep them for the later discussion. And while I introduce Wenfu, please start sharing your screen. So the next speaker is Wenfu Tang from AECOM, and she will talk about comparing the regional scale model variability of Musica with a regional model Wolfram over coolers. Go ahead, Wenfu.
Thank you, Simon. Can you see my screen?
Yes.
Okay, I assume that you can. Good morning, everyone. Today, I will talk about the Musica's capability of representing the regional scale features by comparing Musica to a widely used regional model at regional scale. And before I start, I'd like to acknowledge all my co-authors as listed here. So as we know, Musica version 0 is a global model with regional refinement. And this allows us to study the atmospheric chemistry at all relevant scales. And before we go ahead and apply Musica version 0 to regional scale studies, a key question to ask is that can Musica represent the regional scale variability and features? And how does it compare to regional models? So the short answer is yes. And Musica version 0's capability of representing the regional scale features is comparable to that of Wolfram, which is a widely used regional model. And to demonstrate that, here we compare Musica version 0 with two Wolfram simulations. So let's look at the Musica version 0 simulation configuration first. So we run Musica version 0 for August and September 2020 with a standard grid, and which has the regional refinement over corners as shown here. And the model configuration is listed on the right. So basically we use the FIN version 2.5 for fire emissions, EPA 2017 NEI for anthropogenic emissions within corners, and CHEMS version 5.1 for anthropogenic emissions outside. And we use Mozart TS1 and MEM4 for gas phase chemistry and aerosol schemes. And also wind and temperature are nudged to mirror 2. And all this analysis is based on the 3-hourly output. And for Wolfram, we compare Musica with two Wolfram operational runs at NCAR, and they are named as FireXEQ and AQWatch. So on the left of the slide, I'm showing the domain boundary of the Wolfram runs in red lines and overlaid on the top of the Musica grid, shown with the black lines. So the two Wolfram simulation runs are in forecast mode, and they use Wacom for boundary conditions. And there are two major differences. The first one is FireXEQ uses Mozart 4, where AQWatch uses Mozart T1. And FireXEQ uses EPA 2014 NEI emissions, while AQWatch uses the EPA 2017 NEI emissions. And both runs use FIN version 1 for fire emissions. So as we have seen, the Musica and Wolfram results are from the optimal configurations for each model, and therefore they have difference in the emissions and physics parameterizations, and also slight differences in the chemical mechanisms. Therefore, the comparisons of the absolute amount are not representative here. And in addition, the goal of this analysis is to understand if Musica can represent the regional scale features. Therefore, the following results will focus on the spatial and temporal variability from both models at regional scale instead of their absolute values. So I will only show a few comparisons here today for the sake of time, and here is precipitation. I'm showing the distribution of the temporal variability in precipitation from Musica on the left and Wolfram on the right. And besides this West Coast region, the temporal variability in the two models are similar. And in addition, this figure also shows that there are issues on the Wolfram domain boundary, because as we can see, the temporal variability near the four edges are all very high. And here I'm showing the spatial variability of precipitation in Musica and Wolfram at different spatial scales. So in each panel, a different spatial scale is shown. As we can see, the spatial variability from both models are comparable at these scales. Interestingly, at quarter degree spatial scale, Musica has even higher spatial variability in precipitation. And here I'm showing the spatial variability of ozone in Musica and the two Wolfram simulations. So the top row is for the free troposphere and the bottom row is for the PBL average. And similar as before, each panel is for the spatial variability at a different spatial scale. And the first box is Musica and the rest two boxes are Wolfram. So as we can see, Musica can represent the regional scale variability in ozone reasonably well compared to the Wolfram. And here is the same figure, but for PM 2.5, and the conclusion is also valid here for PM 2.5. And here I'm showing the distribution of temporal variability of ozone. The top row is Wolfram, the bottom row is Musica. And on the left is free troposphere, on the right is PBL average. And overall, the spatial distribution, the magnitude of the temporal variability from both models are close. And the difference here in this region is due to that Musica has a better representation of stratosphere conditions, which is important for stratospheric intrusion. And here is the same figure, but for PM 2.5. And the conclusion is overall valid here, but the difference in this Pacific Northwest region is likely due to the difference in the fire emissions. I've only showed a few cases in the Wolfram and Musica comparison, and I hope I convince you the conclusion is that the Musica version 0's capability of representing the regional scale features is comparable to that of Wolfram. And I would also like to take this opportunity to share another study that I've been working on, which is develop, evaluate, and also apply Musica over Africa. And here is a model grid that I created for Africa. And it has a regional refinement of with a quarter degree over the continent. And I've successfully run the model for 2017. And I'm currently evaluating the model over Africa with in situ observations and also satellite products. And here I'm also using Wolfram as a reference here. And here are two examples showing the comparisons. Long story short, so far the performance of Musica over the region is comparable to Wolfram, and I'm doing more evaluation here. And if you are interested in this study, please feel free to contact me. And I will stop here for with the take-home message. And thank you for listening.
Thank you very much, Renfu. Very nice. Again, if you have questions, please place them in the chat. There's already one for you, Renfu, to answer. And then there will be more discussion afterwards. And while I introduce Doug, please, can you share your screen? So the next talk is by Doug Kinnison and also Jun Zheng with the title Influence of Asian Summer Monsoon Eastward Shedding, Events on Upper Troposphere Chemical Composition. I guess you have a little different title. I just read the other title.
Yeah, I think I might have changed it.
Oh, that's fine.
Do you see the screen then?
Yes, it's good.
Okay.
Go ahead. Thank you.
Yeah, this talk, 10-minute talk, is going to give a summary of a study we're working on looking at the ASM influence on chemical composition of the UTLS using a specified dynamic CCM or Musica. And it's in support of the ACLIP mission, which is an aircraft mission we're going to have this summer in August, based out of Korea, called ACLIP. It's the Asian Summer Monsoon Chemical and Climate Impact Project. It's led by Laura Pan and Paul Newman, and it's a 2-aircraft project, the G5, NSF G5, and the NASA WB-57. Oh, there we go. Again, the model we're going to use is Musica, and we've been talking about that this morning. We have 2 versions of it, the 1 degree and the 1/4 degree regionally refined. I'm only going to show results from the 1 degree today. And the version we're going to use is the 58 level, which has 500 500 meter vertical resolution up to the upper troposphere, and it's nudged by NASA MERA 2. And this model, of course, has detailed interactive tropospheric and stratospheric chemistry. So a really quick background on the Asian summer monsoon transport. The anticyclonic circulation is set up every year in the Northern Hemisphere summer. Within the ASM, surface emissions are influenced by convective uplifting to the upper troposphere and then dispersed into the Northern Hemisphere eastward eddy shedding events. And so we have 2 simple questions here. We want to know what the magnitude of the eastward shedding events are on chemical species into the free troposphere, and 2, how does the interannual variation of the ASM eastward shedding events impact this process? So for this study, we're looking at 6 years. We're looking at 2016 through 2021. We're only going to focus on 150 hectopascal level today. That's where the G5 is mainly going to be flying. We've looked at about 10 species so far. I'll show just CO and PAN results today. And in the next slide, I'm going to highlight some chemistry on PAN and how it's formed by NO emissions. So quickly, PAN in the lower troposphere is thermally decomposed, and until you get up into a region where the temperatures get colder and this process slows down. And then eventually it is photolyzed when you get into the upper troposphere, lower stratosphere. But there's a sweet spot region here where PAN can form. And once it forms, it has a lifetime of about 1 month. So it's a good tracer of air coming out of the ASM. And also it'll be transported into the free troposphere where it can release its NOx and eventually form ozone. And this has been studied by other groups, and the references are below. So what do these eastward shedding events look like? These are 2 examples. On the left is CO and on the right is PAN. This is a year 2020, which we had a large number of eastward shedding events. These are anomaly figures such that you can see that the colors here are carbon monoxide and or PAN. And there are events that are going from the bottom, which is middle of July, to the top of the figure, which is the end of August. And there are 1, 2, 3, maybe 4 or 5 large events in 2020. If you look on the right, you see the same signature in PAN, which is exciting. Now, we know that PAN, again, is formed from NO emissions, lightning, and or surface emissions. However, if you were to have your mission in 2016, it would look very different. And what I didn't mention is that the dashed lines are where the aircraft is actually going to be measuring constituents, these dashed vertical lines. And you can see in 2016, especially if you're in August, you're not going to see a lot of large eastward shedding events. There are small numbers of them, but it'll just look different. You're not going to get the same impact. So we're somewhat hoping for a 2020-like experience this summer. And you see both the low amount of eastward shedding CO and the low amount of PAN for this year. Okay, so to be a little bit more quantitative, what we're going to do is we're going to look at PDFs of these processes. So this is an example of one day in August. This is August 28th, 2021. This is a figure that Ren Smith made. And this is for PAN. And you can see several things on here. One, the white line is a GPH value that kind of outlines the anticyclone of the Asian summer monsoon. The black line is the tropopause at this pressure altitude of 150 hectopascals. And so above the, and on the right here are PDF values. Don't worry about trying to look at the individual PDFs, but just look at the mean, which are the dashed lines here. So if you look at the light blue color here, this is the stratospheric side of the ASM anticyclone. So it's on the other side of the tropopause. There's very little amount of pan in this region of the atmosphere. If you look in where this dark blue mean is here, you can see that there is some shedding that has spread down into the tropics, subtropics, but in general it's pretty low. So this is below, it's not included in the white line of the GPH, and it's below the tropopause, and that's what the blue line is. Now, if you look inside the ASM anticyclone, it's everything inside the white line here. The mean is somewhere around 500 parts per trillion. And if you just want to focus on the shedding region, which is this region right here, which is between 125 east and 175 east inside the white line, its mean is also very high. In fact, this time it's actually greater than the mean of the whole ASM. So what we're going to do is we're going to derive a PDF for every day of the period from July 15th through August, and then we're going to make some histograms and show you just kind of the final conclusion on this. So this is the CO distribution histogram. And again, the light blue is outside the ASM in the stratosphere. The dark blue is outside the ASM in the troposphere. The gold is what's inside the ASM everywhere. And then the red is only in the shedding region. And there are, the horizontal axis shows every year that we looked at. The red line is showing the minimum value in the shedding region. So right off the bat, you can see that within inside the ASM is similar across all years for CO. There's a little bit of variability, but not that much. If you look at, however, what's in the shedding region itself, the red bars, what you see is that the maximum year is 2017. There are a couple other years that are similar to that, and the minimum years are 2016 and 2018. The difference between the max and the min is about 30%. So depending on which year you pick, you're going to have about 30% more or less influence of the ASM eastward shedding events in the region where we're actually going to be measuring CO. If you look at NO, again, NO is produced from surface emissions and also from lightning. Inside the ASM, the gold part here, it does vary with time. It actually builds up such that you can have, the emissions can have 35% higher values, say in 2020 versus 2017. When you look just in the shedding region, which is the red, the max and min years, there's a roughly 61% more NO that can be produced depending on which year you pick. And then finally, the influence on pan, same kind of figure. In this case, the shedding region has up to 73% more pan in a year that's very active with eastward shedding events versus a minimum year like 2016 or 2018. So going into this, I wasn't really sure what these values would be, but you can see that it does matter, and that the dynamics of the year does really set up either a lot of pan, a lot of NO, or NCO, or not. So in summary, we've taken a look at eastward shedding events, and we've seen that they do have a large interannual variability. This variability will impact the airborne emissions like ACLIP. We've examined 6 years and found significant variability in several species. NO and PAN show more variability than what you see in CO. And we still need to quantify the different emission sources of NOx, for example, the surface emissions versus lightning. And one way to do that is we have tag mechanisms that Louise Emmons and others have worked on that we could apply to this problem and really follow where the NOx is coming from which process. The export of pan will impact tropospheric ozone production. This has been discussed in multiple studies, and we'd like to follow that ozone production and quantify that in the future. And we can do some tagging on that also. So in summary, we have a little bit more work to do on this project, but we are looking forward to a very exciting airborne mission this summer. Thank you for your attention.
Thank you very much, Doug. Very interesting talk. Again, put your questions in the chat or wait for the final discussion. We have one more talk in this session by Ren. Ren, could you please start sharing your screen when Doug stops sharing? Yes, and then I will introduce the last talk by Ren Smith from ACOM. He's talking about evaluating the representation of Asian summer monsoon UTLS composition in CSM using airborne and in situ observations. Ren, go ahead.
Okay, thank you, Simone. Can you see my slides? Everything look okay?
Yeah, I think we can see them fine.
Okay, awesome. So thank you. So like Simone said, my name is Ren Smith. I'm a postdoc working in the ACOM lab at NCAR. So the goal of this work is to characterize how CESM is representing the upper troposphere, lower stratosphere during the Asian summer monsoon. And this work has been really helpful for us in helping prepare our NCAR model configuration for the ACLIP field campaign, which Doug just mentioned and nicely set the stage for me on, which is going to take place in August from South Korea this summer. So Doug kind of mentioned actually a little bit of the background here, so I can kind of gloss over that a little bit quicker, but basically the coupling between the anthropogenic emissions in Asia and the deep convection that's associated with the summer monsoon precipitation has been shown to have a pronounced effect on the composition of the upper troposphere, lower stratosphere in this region. So this mechanism drew interest for the Stratoclim aircraft field campaign, which took place in the summer of 2017 over South Asia, and that's what we're going to be using for the present evaluation, mainly because we're waiting about 2 years now for ACLIP observations because of the pandemic. And so this is a really useful data set for us over South Asia while we're waiting. The flight tracks for the Stratoclim mission are shown here in the black lines there. So we evaluate two different configurations of CESM. We have a Musica simulation, which has the horizontal regional refinement over Asia. And I think we've seen this grid a couple of times here now, but this is sort of the Asia grid that's been developed with Musica for this purpose. And then we also have a 1 degree Wacom simulation, which has 110 vertical levels. And this reduces the vertical grid spacing in the UTLS layer to about 500 meters. So looking at these two simulations allows us to look at the potential benefits that the improvements in these sort of spatial resolutions can translate to in their representation. So for starters, I want to look at maps of carbon monoxide here, which is a tropospheric tracer. So we have Wacom on the left, Musica on the right, and then we have 70 hectopascal on top, which is representing the lower stratosphere, and 150 hectopascal on the bottom, which is representing the upper troposphere. So what we see is that at both of these levels here, the regionally refined Musica simulation on the right is lofting more CO into the UTLS than Wacom. And we think that that's a direct result of the refined horizontal grid. So it's interesting to see this sort of direct translation of this tropospheric tracer and the differences there, just with the difference in the horizontal grid. Obviously, this is really interesting to know, but the obvious follow-up question is more CO necessarily better? Is it getting us closer to observations? And so that's where we bring in the observations. I'm looking at this observations and models in a vertical profile space, specifically a tropopause relative altitude space here on the left. The grayscale pixels are showing the observations as a layer normalized relative frequency. And then we have the Musica simulation in red and the Wacom simulation in orange. So the solid lines are the means and the dashed lines are the 5th and 95th percentiles of the model information. So it's important to note here that the model information on this plot is actually subset over the gray box that's on the map on the right, and that's during the entire measurement time period and over a much larger, so it's over a much larger spatial and temporal region. So with that in mind, the fact that the general behavior of the model and the observations falling reasonably in line with each other is very reassuring that we're representing the general behavior of this region. So to compare the specific models to each other rather than just against observations, I want to call out two specific layers that are on this plot. The first one is approximating the primary level of convective outflow. So that's shown here, or the layer that I'm choosing here, subsetting, is the gray dashed lines here, or is bounded by the gray or black dashed lines, sorry. The mean values of the distribution are printed in the legend here on the distributions on the right. So we have the observations in black again, Musica in red, and Wacom in orange. And we can see that in this layer, neither model has quite as much CO as the observations, but nonetheless, the enhanced CO in the music simulation, just like we saw on the last slide, is actually indeed constituting an improvement compared to observations at this primary level of convective outflow. And then the other layer I want to look at as well is in the lowermost stratosphere. This is 1 to 2 kilometers above the local tropopause. The music simulation, again, is falling closer to observations than the Wacom simulation. And it's worth noting, actually, looking at the shapes of these distributions, that subjectively, at least, Wacom seems to struggle with the shape of that CO distribution compared to observations, and really skews towards the very low CO values in this layer. So calling that layer into question there in that simulation. That being said, the next evaluation is going to be looking at some tracer relationships. And so what I'm showing here is ozone versus CO relationships, Wacom on the left, Musica on the right. And the models are shown as the pixel data, and the observations are shown as very small black dots, so I don't cover up the model too much. One of the key things to note on these plots is the difference between the models in their stratosphere to troposphere transition, which I'm showing here in red. And this actually appears to be better represented by the Wacom simulation. And this actually may be due to its enhanced vertical resolution in the UTLS, which may be better resolving that transition. So, we see some benefits, or it seems that we see some benefits to the horizontal regional refinement. We seem to see some benefits to the enhanced vertical resolution. And so the impacts of these different decisions certainly need to be carefully weighed, and can both have influence on the resulting simulation. We've also looked at how different models perform in a chemical coordinate space. So here we're using CFC11 as basically a chemical vertical coordinate because it is well mixed throughout the troposphere, and therefore can be used to indicate the depth in the stratosphere. So this slide is showing a collection of relationships in the CFC chemical coordinate space against species that range in lifetime from a decade to a century. So fairly long-lived species here. And all of them are really excellently represented by the models when you compare the black lines to the red and the orange lines. So this gives us confidence that the chemistry mechanisms, as well as the sources, the sinks, et cetera, of these species are being properly represented in the models, and that makes us confident that this model, or the model configurations, are trustworthy for characterizing the impacts of these species on the summer monsoon in a, whether that be in a past, present, or future sort of setup. And then there are other relationships against CFC11 with the shorter-lived species, which sadly don't show the same kind of neat consistency. And we think that's probably because these species have lifetimes on scales, ranging from, in this case, a few months to a few years, scales that may be influenced by convective activity, and that is obviously parameterized in the simulation. So we're not going to see quite as nice of a consistency as we saw with the longer-lived species. But the main point that I'm going for here is that this chemical coordinate diagnostic that we've established here allows us to easily identify species which are not up to snuff compared to observations over the monsoon, and that showcases the strength of this approach towards model evaluation. So an example of this is that in the bottom row here, we have some methyl halide species, methyl chloride and methyl bromide, that seem to be really missing the mark compared to the observation. So with a little bit more digging into those species, we actually found that both of those methyl halide species are using zonally averaged emissions in the model. So it makes sense that the models would be too low compared to observations, since the maximum emission values over Asia are actually getting smoothed out in this zonal average. So to really prove this and hammer this home, we actually plotted airborne observations that were taken over the CONUS in blue. So those ones are in blue. The Asia observations from Stratoclim are still in black. This tells us that our models over Asia are conforming very nicely to the background observed values of these methyl halides. And this tells us that the model transport here is actually working excellently, but the issue with these species is with the emissions. So the takeaway here is much bigger than just a need to fix our emissions in these species, though. It's that we can establish this chemical coordinate diagnostic, and that has allowed us to identify certain problem species and actually isolate the root cause of why they're not being represented compared to observations. And so that shows that this could be a very powerful tool. And then finally, I'll end with take-home messages. So probably the most, or one of the more important things here, generally broadly speaking, is that these CESM configurations, Musica and Wacom, are generally representative of the distributions of chemical species observed within the Asian summer monsoon UTLS during the Stratoclim campaign. We've established this diagnostic framework, and it's allowed us to infer and hypothesize some things about sort of how the model's representing the monsoon region, enhanced lofting of CO by Musica, better troposphere stratosphere transition in the Wacom simulation, as well as representing the long-lived relationships very well. And then finally, just to say that the diagnostics herein most broadly can be applied to characterize the performance of other model configurations as we try out new configurations, or potentially at representing atmospheric behavior in other parts of the world. So I think I'm just about over time here, so I will end there and say thank you for your attention.
Thank you very much, Ren. That was right in time. And first of all, I want to thank all the speakers for this session very much. Thank you for staying so much on time. That worked out really, really well. And now we're starting our discussion. If you want to turn on your cameras, that's great. If not, that's okay too. So we do already have 2 questions for Ran. And since Ran, you are right here, why don't we answer those first while people think about other questions? And Wenfu has already answered some questions in the chat. So I don't know if you see the chat. Ben, you can ask your question if you want, and then Rich maybe. Ben, are you there? I can also read it.
Hi. I was just wondering if what emissions were you using, and how can you compare CO in a way that you take into account the different resolution, and that maybe you could look at anthropogenic CO only, since you may have different CO with the different vertical and horizontal resolution.
So we're using the CAMS emissions for these, and we do have tag CO, so we can take a look at that in more detail. But that's a really good point.
Yeah, we look at that for the ACLIP sort of in the forecasting configuration that we have. A lot of times when we're trying to forecast where to fly, we have these tagged regions for different parts of Asia. I haven't looked at those for my particular purpose. For what I showed, but that is actually a really interesting idea. So thank you for that.
Yeah, because you're using biogenic online biogenic emissions, right? So that would be different.
Right.
And also using QFED then in the forecast for biomass burning.
Yeah.
I believe it's QFED.
Yeah,
it is. Yeah.
Okay.
And Rich, you have a question for Ren? And others, raise your hand if you have other questions, then we go on, or put some in the chat while Rich is asking his question.
Yeah, thanks. Yeah, it was a nice talk. I'm just wondering, the contrasting the Musica, regional refined versus Wacom higher vertical resolution, whether it's obvious that the meteorology is leading to, greater transport into the stratosphere, and whether it's clear that, increased horizontal resolution, it makes that more likely or not.
Yeah, that's a really good point. I think there's probably a little bit more work to be done to really confirm that it is in fact the higher horizontal resolution, like you say. I believe there are some variables, and I'd have to check and see if we output them in those simulations, but there are some variables that we can output to actually check. I think there's some kind of a proxy for convective detrainment or something like that from the Zhang-McFarland convective scheme. And it would be interesting to look at that from the different simulations to see if that's really what's leading to that deeper vertical transport in the Musica simulation.
Yeah, I mean, that'd be super interesting to look at, because I know that the precipitation and implied convection in the regions in the Himalayan foothills is very sensitive to horizontal resolution. So that'd be really good to look at. Thanks.
Yeah, definitely. Thank you for that.
Yeah,
In addition to that, we have run, he was showing the 32 level, I believe. We've run the 58 level, and that's And you get even more CO going to higher vertical resolution.
Uh-huh.
But there's some interesting features with, I think it's based on the convection, that there's maybe a little non-conservation going on. And so we wanted to talk with you guys a little bit
Okay,
about
yeah.
this. And it's not a big issue, but it's one that we want to correct if we can.
Yeah, and that's the reason I chose to show the 32 level for some of those chemical relationships, but there's still some things we don't quite understand, but be interesting to look at that.
Okay, thanks. Rafa, you have your hand up. Go ahead.
Yeah, thank you. So this is for Brian or Doug. I found really interesting this not well performance on reproducing methyl chloride and methyl bromide, and this relation with the lower boundary conditions. Actually, this is something we've been doing for even short-lived species than those. Are you planning on including like just increasing lower boundary conditions or using like an emission inventory for those species? And I remember for methyl bromide, at least, there was initially a hemispheric lower boundary condition, like northern hemisphere and southern hemisphere. But then in the latest versions, there is like a stronger latitudinal distribution. In our halogen simulations, usually the northern and southern hemisphere conditions work better than this latitudinal distribution, at least in the past.
Yeah, I can comment on that. So these two species have mole fraction boundary conditions. They're not emission boundary conditions, and we get the mole fraction boundary conditions from scenarios like from CMIP6. We would need to, which I think is what you're implying, is switch to emission boundary conditions if they exist. The CMIP6 boundary conditions do tend to have a latitudinal gradient, but again, they're zonal mean as Ren has specified. So we just would need to improve our boundary condition set if we can find a good emission inventory.
Okay, thank you, Doug.
Thank you. I would have a question. Don't see anybody else right now for Nori. And so Nori, you showed the change in biogenic emissions, and you changed them 25, 50, 75%, but you focused on the Colorado area. What happens then? Do you look also globally what happens, or can you actually, you cannot change them just over one region, right? You have to change them globally. Would that help the performance, or have you looked at that?
For right now, I've only looked at the Colorado region, but I mean, it would be, to be honest, I haven't really taken too much of a look over the entire globe. Yeah.
Yeah, because I think I think we do have some overestimation. I think it's some parts of isoprene, maybe Louisa, also. But I do wonder, how do we tune those? Is there a way, or is it somewhat, how do we improve those instead of just, I mean, the sensitivity studies are very interesting, but how do you actually integrate it for the global model?
Yeah,
so I mean, go ahead, Lisa.
It's definitely a challenge. And I think, I think maybe we have seen isoprene overestimated in other regions. I think it can depend quite a bit on the vegetation map. So that was one idea. We had to improve the resolution of the vegetation map. And it's hard to evaluate isoprene because it's so short-lived. There are not a lot of measurements, and you have to have it in a specific region. So it's definitely a challenging thing to optimize.
Any other questions? I would have a real quick question for Doug, but I also want to move on. We can discuss. I'm just really interested in the variability of the shedding, and I wonder if that has some climatic connections, what is causing this? But I guess that's not a short answer.
Yeah, the dynamics that's causing the shedding, year-to-year interannual variability. I'm probably not the right person to answer that question. But you have different ENSO signatures on it, I'm sure. And Laura Pan and others have even talked about the influence of typhoons coming in, the frequency of those in cyclones. So, something to figure out, because the frequency is very different year to year.
Yeah, certainly very interesting to look into, I think, too. And I think we end the session now, and I give it now to Nick, and that he can start right in time. Thank you.
Okay, thanks. So we'll move on to the next session. This will be the same format, 10-minute talks followed by a question and answer session at the end. So first talk is Sudha Kamali. Can you go ahead and share your screen? And it's development of SC Wacom with the non-hydrostatic MPAS-A dynamical core.
Good morning, everyone. Do you see my slides, Nick?
Yes, it looks good. Go ahead.
As Nick mentioned, I'm Sudha Kamali, and I'm an ASB postdoc here at NCAR. And today I'd like to share with you some of the work that we've been doing in the development of SC Wacom with the non-hydrostatic MPAS-A dynamical core. And this is a joint effort between MCube and HAO. From HAO, I've been working with Hanli Liu and Francis Witt, and from MCube with Bill Skamarok, Joe Klemp, and Peter Lauritsen. Here's an outline of the talk. I'll briefly mention the motivation behind this work, and then we'll talk a little bit about the dynamical core configurations, and then I'll share with you some of the climatology results from the simulations that we've done. And in order to explain some of that results, we've done some preliminary gravity wave forcing analysis that I'll present as well. And as you might already know, geospace applications require atmospheric models with tops in excess of 500 kilometers. So for example, Vacuum X extends from the Earth's surface up to approximately around 600 kilometers. And in these regions, the accuracy of the hydrostatic approximation becomes problematic. And so there's an increasing need for whole atmosphere models with non-hydrostatic dynamical cores. However, at the moment, the dynamical cores available to Vacuum X are all hydrostatics. But recently, as part of the CEMA efforts, NCAR has been adapting MPAS-A, the model for prediction across scale atmosphere, to work inside of CESM. And this will bring non-hydrostatic modeling capabilities to CESM, and it opens up the opportunity for us to be able to use MPAS-A with Vacuum X for geospace applications. However, the first step towards that would be to just get Vacuum running with MPAS, and that's what we've been working on and what I will be presenting on today. So the dynamical cores that you're probably used to using with Vacuum are the FV and the SE model. And as the name suggests, the FV model is a finite volume solver, and the SE model is a spectral element solver. The FV model uses a lat-long global grid, while the SE model uses a cube sphere mesh. They're both hydrostatic models, and they both use sigma pressure vertical coordinate. Now we also have the option to use MPAS with Vacuum, and MPAS uses centroidal Voronoi mesh, and as I mentioned, is a non-hydrostatic model. It is a finite volume solver. However, it uses a C-grid staggering, while the FV model uses the D-grid staggering. And for the vertical coordinate, we're using a hybrid train following height vertical coordinate in MPAS. So in addition to being a non-hydrostatic model, the differences in the horizontal staggering of the variables and also the vertical coordinate, and also some differences in the filtering configuration could affect the results of the simulations. And to evaluate and validate that if Vacuum was running properly with MPAS, we decided to set up a case with SC Vacuum for each of the different dynamical cores for a 1-year simulation on a 1-degree mesh, and then compare the climatology results with each other. And I'd like to mention for these simulations, the parameterized gravity wave forcing produced by frontogenesis was disabled. And we looked at mean zonal wind and temperature climatology. And here I will only be presenting the mean zonal wind climatology for the benefit of time. And before we look at the simulation results, I just wanted to point out some background on the climatology. So I have here the climatology for June 92 and January 93. And what I want to point out here is the wind reversal that we see near the mesopause area. And what's interesting about this wind reversal is its asymmetry. It's asymmetric in both height and its strength. And we can see that in both June and January, the wind reversal for the summer hemisphere happens at a lower height in comparison to the winter hemisphere. And also the strength of the wind reversal is bigger in the summer hemisphere. And this asymmetric zonal wind reversal near the mesopause is known in both climatology and radar observations. However, it's difficult to reproduce in parametrized models. And I'd like to just point that out before we move forward and looking at the results from the simulation. So I have here the mean zonal wind climatology from the 3 dynamical cores running SC vacuum with FV, SE, and MPAS-A. And at the bottom, I have the climatology for your reference that we had on the previous slide. And this is for the month of January. And when we look at the winter hemisphere, we don't really see that reversal that we see in the climatology. We see a slowdown, but not a reversal. But when we look at the summer hemisphere, we see that MPAS was able to reproduce that wind reversal. In the case of the SC and FV, we do see a slowdown of the jet, but not a reversal. And so in the strength of the reversal is much smaller than what we see in climatology, but the location of it is roughly at a good place. And in order to explain this reversal that we were seeing in MPAS, we decided to do some gravity wave forcing analysis. And here is the total parametrized gravity wave forcing, which we first look at. And as I mentioned, this is for month of January. At the top, we have the parametrized gravity wave forcing for the FB, SC, and MPAS. And at the bottom, I've put the corresponding mean zonal winds for each dicore for your reference. And we can see that where we're seeing this wind reversal in MPAS and also the slowdown for the SC and FB, we don't really see much activity for the parametrized gravity wave forcing. And that was to be expected because, as I mentioned earlier on, we've turned off the frontogenesis function. And so we don't have the effects of the parametrized frontal gravity waves, which are the main contributors in these regions. And so if it's not the parametrized gravity wave forcing that is giving this reversal, we thought, well, maybe it's the resolved gravity wave forcing. And so we've diagnosed the resolved gravity wave forcing using the transform or Eulerian mean method. And at the top, you have these resolved gravity wave forcing for the FV, SE, and MPAS dynamical core. And at the bottom, I have the mean zonal wind for the corresponding to each dynamical core. And this TEM method will allow us to look at both large scale and small scale gravity waves. And so when we're looking here, we can clearly see an eastward gravity wave forcing corresponding to the eastward wind reversal that we see in MPAS. And it's similar where we see the slowdown in SC and MPAS, we are seeing these gravity wave forcing appear. And so we can clearly see that it is the resolved gravity wave forcing that's creating these reversals. And if we look more closely at this region to try and see what's the difference between the resolved gravity waves between the 3 dynamical cores, we have here the vertical profile of the resolved gravity wave forcing, and we can see that for MPAS at a lower altitude where that reversal is happening, is the forcing is much stronger. And although we see a strong forcing for the FB and SC, that's happening at a higher altitude, and so and that's why we're seeing these reversal in MPAS. And this is very preliminary studies. And in order to really understand the difference between the resolved gravity wave forcing between the 3 dynamical cores, we will have to do a further study and investigation. But we wanted to just share that with you here. And in summary, as part of the CEMA effort, we have developed and tested the SC vacuum with the non-hydrostatic model for prediction across scale at MPAS-A, and the mean zonal wind and temperature climatology for SC vacuum MPAS-A compares well with the results from SC vacuum using the FV and SE dynamical cores. There are certain differences between them, and in order to study that, we have looked at some gravity wave forcing. We've done some analysis there, and we've realized that a lot of the differences is coming from the resolved gravity wave forcing. However, in order to really understand these differences between the models, we'll have to do further study, perhaps some spectral analysis study. And I'd like to mention here that this was the first step, as I said earlier, towards the main goal for us, which is to adapt the non-hydrostatic deep atmosphere MPAS-A to work with Vacuum X. So thank you for your time, and we'll be happy to answer your questions in the Q&A section of this session.
Okay, thank you, Sudha. As we mentioned, either put your question in the chat or save them for the question and answer at the end of the session. So our next talk, Tao, could you go ahead and start sharing your screen? Will be given by Tao Wang, and it is the parameterization scheme of thermospheric gravity waves in WACAMX. And we can see your screen. It's not in the presentation mode yet.
Okay.
Okay.
Thanks, Nick.
So please
hi
go
everyone.
ahead.
Okay. Hi everyone. I'm Tao, a PhD student in London University and a visitor in NCAR HO. I'm very glad to give a presentation in CESM Workshop. And today my topic is the thermospheric gravity wave parameterizations in WACAMX. And we know the dissipation and the propagation of gravity waves is important throughout the whole atmosphere. And in the lower atmosphere, the lower and mid atmosphere, the dissipation is mainly due to the wave breaking. And in the upper atmosphere, we can see with the increasing kinematic viscosities, the molecular damping plays an important role on the dissipation of gravity waves in the thermosphere. For the current WACAMX, this is a FA WACAMX. We can see there's a large forcings near the mesopoles due to the wave breaking effects, and it's implemented by the Lindzen saturation theories. And there's the molecular damping effects are not well considered in the thermosphere in the current WACAMX. So this work will aim to develop a thermospheric gravity wave parameterizations in WACAMX. We use the governing equation, Bosnian governing equations, and the viscous term, including kinematic viscosity and thermal diffusivities, is on the right hand. And the mu is the kinematic viscosity, and eta is the thermal diffusivities. And note the Coriolis force and the ion drag are not neglected in these studies. And the viscous, we can derive the viscous dispersion relations from the above governing equations, and using these 5 definitions and hypotheses. And note the imaginary of vertical wave numbers MI plus the inverse decay rate. And when we use the first 2 definitions, we can get the dispersion relations is the same as the equation 19 in Vadas and Fritz in 2005. And our dispersion relations is it can be separated into the real and the imaginary part of and into imaginary part and the real part. And we use the iterative method to get the solution of MR and MI. So here are the solutions for the MI skew height with a 100 kilometer horizontal wavelength. And as a function of intrinsic phase velocity and the height, we can see the MI skew height is rapidly decay with the increasing kinematic viscosities. And the red dotted line denotes the dissipation height, where the period of molecular damping equals to the period of gravity wave. And we can see it's grows with the increasing phase velocities. And the blue steeple field is the total wave reflection regions, where the gravity wave frequency is larger than the Breuer frequencies. And here are the solutions for MR. To easily understand, we calculated the MR into the vertical wavelength. And the left figure shows the vertical wavelength considering molecular damping. And we compare it with the vertical wavelength without molecular damping. And we can see the vertical wavelength is the shorter vertical wavelength is damped, and the longer vertical wavelength is saved with the increasing kinematic viscosities. And here we develop a column WACAMX model to present the upward propagating gravity waves at 60 degrees north. The zone mean temperature and zone wind at 60 degrees north in January are set as the background fields, and the Gaussian gravity wave source from the ground-based phase velocity from -100 to 100 meter per second are launched at the troposphere. And the momentum flux due to the molecular damping is defined here. Here's the vertical profile of a momentum flux only due to the molecular damping, and for the specific wave speed, phase speed, and the left is the westward phase speed, and on the right hand is the eastward phase speed. We can see the wave stop propagating when they reach the critical layer, and in general, the faster wave speed and has a higher altitude of the inflection point. And here we have the vertical profile of zonal forcings for the summary of the wave spectrums, phase spectrums, and the solid line is the molecular dampings. The dissipation only due to the molecular dampings, and the dashed line is only due to the wave breakings, and the black line is the phase velocity from the -100 to -100, and the red line is the phase velocity from -60 to 60 meter per second, and the red line is the blue line minus red lines. We can see there's the westward forces near the mass force, mainly due to the lower speed gravity waves, and we can see the molecular the forces due to molecular damping is larger than the wave breaking. Which implies that the molecular damping may contribute to the zonal wind reversals near the mass pulse. And in the thermosphere, we can see the eastward forcing is shown occurs due to the molecular dampings, and the faster phase speed has a higher peak height in the thermosphere. When we consider both the molecular damping and the wave breaking effect, here's the vertical profile of zonal forcings for the for both consider the molecular damping and wave breaking effects. And we set the wave force at the troposphere, and we take the minimum value of tau by wave breaking and molecular damping in the lower and the mid atmosphere to remain the forcings unchanged there. So we don't want to change the forcings in the lower and mid atmosphere. And for the thermosphere, we only consider the molecular damping in the thermosphere because the Lindzen saturation theory is no longer active in the thermosphere. And when we compare it recently, when we compare it with the SE vacuum max results, we can see the peak height. The peak height is around 250 kilometers in SE vacuum max, which is the gravity wave is resolved in the SE vacuum max. The altitude is higher than the parameterization results, so which implies that the thermospheric gravity wave forces is not only originated from the troposphere, but also they can originate from the mid and higher altitude, which is closer to the secondary wave series. So we are working on a set wave source with a wider phase velocity in the mid and upper atmosphere to get a higher peak altitude and closer to the secondary wave theory. Here and some summaries. The properties of gravity wave in the thermosphere, including vertical wavelength, inverse decay rate, and dissipation height, is derived from a viscous gravity wave dispersion relation. And the large wave forcing in the thermosphere occurs in vacuum max, implemented by a thermospheric gravity wave parameterization, and the forcing in the lower mid and atmosphere remain unchanged. We are working on a new scheme which is closer to the secondary theory to more comparable with SME vacuum max. And the full vacuum max model results, including the thermospheric gravity wave forcing and effective vertical diffusion will be performed in the future to reduce the model bias. We know for the current FY Wacom-Max, the column integrated auto is more higher than the observations. So thanks.
All right, thank you, Tao. So if you could stop sharing your screen, and Raphael, do you want to go ahead and share yours? So next talk will be given by Rafael Pedro Fernandez, spatial temporal distribution of inorganic halogen sources and sinks in the troposphere, evaluation of VSL chemistry between CSM1 and CSM2.
Okay, you can see my screen now.
Yeah, I don't know if it is just me. I see a sort of box in the bottom. Oh, there it's better. Okay, go ahead.
Okay, thank you very much. So it's a pleasure for me to present these results in the CESM workshop of the inorganic halogen chemistry implementation in CamChem and a comparison between our results in CESM1 and the porting into CESM2. So this work has been developed in cooperation with many groups and people from the Department of Atmospheric Chemistry and Climate in Madrid, Spain, some students working with me here in Argentina, in Mendoza, and also our colleagues from NCAR. So I will split my talk in 3 different subsections. So first, like a technical description of which are the main sources and sinks of halogens in the troposphere. Basically, because we don't only want to compare CESM1 and CESM2 in atmospheric burdens, but also on the sources and sinks. A comparison between natural very short-lived halocarbons with respect to long-lived ozone depletion substances will be given, and also the impact of sea salt aerosol dehalogenation. So then I will present some rapid results of the most important features on this evaluation of CESM1 versus CESM2 and the role of the boundary layer in limiting the transport of halogens from the boundary layer to the free troposphere. And at the end, some nice results we have just published on the impact of chlorine on methane lifetime and burden. So basically, to talk about the contributions, source gases halogen source gases are transported from the surface to the stratosphere. And I will split the contribution from long-lived halogens, those that have a lifetime more than 6 months. And I will have a special attention on methyl chloride and methyl bromide that Ren also provides some results related to the ACLIM campaign. For sure, the contribution of short-lived halogen species, which are photodecomposed in the troposphere. So the long-lived species are assumed to be completely unreactive until the stratosphere, but then the short-lived halogens react in the troposphere and they provide chlorine and bromine atoms, which participate and alters the oxidative capacity of the troposphere. And finally, the contribution from sea salt, this sea salt dehalogenation source, which is further explained in the next slide. Basically, we have implemented in the model this type of recycling based on the free regime approximation, which states that a halogen species can capture the bromide or chloride contained from sea salt aerosol and release those species back to the gas phase. So this was implemented initially only for halogen reservoir species, which could capture and uptake the bromide content or chloride content from sea salt. And in the Lee et al. Paper I will present today, we updated this mechanism for chlorine in particular, because acidification of the sea salt enhances the capture of chloride and then the release of more chlorine to the atmosphere. So this process is strongly dependent on surface area density of the model, and then depending on the distribution, this source, the magnitude of this source changes significantly between different model configurations. So our initial results here, I highlight, this is the chlorine production, so this is the release of chlorine atoms at different vertical levels in the model. We can see that the dominant source in green are the sources arising from sea salt dehalogenation, which is maximized in the boundary layer, but then it also has a great magnitude in the free troposphere. Then in second place, so the contribution from short-lived species is in blue, and we can distinguish the contribution from anthropogenic species and natural species released from the ocean. So basically, the anthropogenic contribution is the only significant one. Mostly, dichloromethane is transported and is releasing chlorine atoms in the free troposphere. But very interesting, we can see that the contribution for methyl chloride, which is here in orange in the troposphere, is even larger than the contribution from the anthropogenic dichloromethane. And let's keep in mind that methyl chloride has mostly natural sources and is not controlled by the Montreal Protocol, and is included in the model as a lower boundary conditions and without any spatial resolution. So that would be really interesting to evaluate in the future, as highlighted before. So the good things is that what we have been able is to quantify which is the most important chlorine source in the troposphere, and basically is mostly sea salt dehalogenation, both for chlorine and for bromine. Comparing CESM1 and CESM2, so this is the same plot on the left for CESM1, and these are the new results for CESM2. What we see is that there is a stronger barrier here in the top of the boundary layer. So sea salt is not transported so efficiently to the free troposphere, and then the magnitude of the chlorine release from this recycling is largely reduced by approximately 14%, which we believe is more realistic representation of the atmosphere. So in comparison, for bromine, which is what we are more familiar with, we can see that this barrier for bromine recycling on sea salt is also present in CESM2, and this is a good thing, a good improvement in the model. But then also that the contribution from natural halocarbons, very short-lived halocarbons, in comparison with the long-lived methyl bromide, is also much important, and this the inclusion of very short-lived species for bromine is really required for the proper representation of bromine in the troposphere. So this is just a comparison of which are the places. I will not go through all of these numbers, but where are the first, second contributions of halogens to the troposphere. So for both cases, for chlorine and for bromine, natural sources are the dominant ones, although for chlorine is mostly methyl chloride and for bromine is mostly bromoform. So this is the final comparison that we have for CESM2. We have now a freeze version of halogen chemistry in CESM2. We can see the plots on the left are results of inorganic chlorine in CESM1, and on the right in CESM2. We can see this small reduction here in the free troposphere due to the sea salt recycling that was too efficient in CESM1 that has been updated. But consistently, we can see that the source gas injection and the product gas injection of organic source gases and inorganic product gases is very similar between the two models, which are here on thick and dashed lines. So lastly, I just wanted to introduce some of these really interesting results of the impact of chlorine on methane, which connects halogens with climate. Basically, all these improvements that I have just mentioned have been implemented in this model. All these results have been performed with CESM1 version of CAMCHEM with halogens. We improved the representation of HCl in many surface around the world, surface observations around the world, which are represented here on the right. And also we have a really nice representation of the vertical profile of dichloromethane, which was the main chlorine source from short-lived halogens. So what's the role of chlorine in methane? So basically, general wisdom says that if you increase an oxidant, which is the chlorine atom, by including all this halogen chemistry, then we will increase the loss of methane by the direct reaction with chlorine with methane. But we have to keep in mind that the main destruction channel for methane is OH. And OH is strongly affected by halogens indirectly because that's one of the main implications that have halogen chemistry in the troposphere. They affect ozone, and altering ozone, then they can change the OH partitioning and abundance in the troposphere. In the clean environments, the inclusion of halogens decrease the total OH abundance, but then in polluted environment, they can increase this. So which of these contributions wins when we include halogen chemistry on methane? We have computed this on the loss rate, like quantitatively. We can see that on continental and polluted regions, there is an enhancement of the methane loss rate, but then there is a very large and significant reduction in the OA and the methane loss through all over the oceans, which has a consequence that the net global burden is decreased. So basically here on the left, sorry, we can see that enhancing the chlorine loss rate increases by 100 or 200% when we include short-lived species in the model. But then this also results in a reduction of 8% of the total OH losses. And this compensates, and the reduction in OH, the destruction of methane by the reduction in OH drives the overall behavior of methane in the troposphere. So we have a lifetime of enhancement of approximately 0.6 JRs. So that is almost 6% of the total lifetime. And we can also see that the burden is increased regardless of the simulation. So this is occurring for RCP 6.0 and RCP 8.5. And that the net reduction in radiative forcing, the net increase in radiative forcing is approximately 0.05 watts per square meter. So that's all for today. I'm a bit past of time, so thank you very much.
All right, thank you. If you could please stop sharing your screen and we can move on to the next talk, which will be given by Sebastian Eastham. Do you want to go ahead and start sharing your screen?
Sure.
And the presentation is GeosChem as a chemistry module in CSM. So we can see your slides, so please go ahead.
Excellent, thank you. First, I apologize if this talk is a little low energy or strange. I've been recovering from a stomach bug for the past 3 days, so I'm a little out of it. But thank you so much for this opportunity to talk. I'm going to be talking today, as introduced, about GeosChem not as a standalone model, but instead now as a potential chemistry module available in CESM 2.1.1. And this is really work that's been completed not so much by me as by my student, Thibaut Fritz, who unfortunately couldn't be here today, with incredible help from collaborators both at NCAR, such as Louisa Emmons and Steve Goldhaber, and at Harvard, such as Haiping Lin, Elizabeth Lundgren, and Danielle Jacob. Before we get started, I just wanted to acknowledge that this work was supported by the NSF, and that we made use of the generous resources at Cheyenne to complete it. So the basic question is, why do this? We have a perfectly good chemistry module in CESM, of course, already in ChemChem, never mind WACCM. And the basic idea is that we want to advance a few different ideals. So we are looking to address the so-called chemistry grand challenge brought up by the National Research Council, this need for chemistry to be an online process in CCMs, and which was not a capability of the GeosChem standalone model prior to this point, really. We want to increase accessibility. That means making GeosChem more available to the CESM community, while also bringing CESM's capabilities through to the GeosChem community. We think that by knitting those communities together through a common access point, we will allow a greater transfer of knowledge and a greater understanding of the relative capabilities and deficiencies of the models in question. We also want consistency to understand why our models disagree, and that's something I'll go on about a little bit more in just a second. And of course, generally speaking, we want to be able to improve our models, and I think that's something that's made possible through efforts such as these. So I wanted to come back to that question of consistency. GeoSchem's ozone is thought to be biased low, whereas relative to this, we think that ChemChem's is not. And this was something that was evident in Park et al.'s 2021 paper, looking at comparisons to the chorus AQ measurements. But at the same time, in some other areas, GeoSchem might get a better fit than ChemChem. And historically, certainly the community that I'm most familiar with, the GeoSchem community, would think of this as being a chemistry problem. But of course, there are multiple possible reasons for this. Could it be because of different emissions inventories, different chemistry, as we thought, or perhaps even different meteorology? And the truth is that when we don't have a common framework in which to test multiple chemical modules, it's difficult to say which of these factors is the case, or if there's a common deficiency between them, which causes different outcomes. So to that end, we have GeoSchem now integrated as a chemistry option in CESM as it stands. This is a downloadable set of code that I'm happy to share with anyone if they're interested, where we have GeoSchem as a parallel option alongside ChemChem. This is the basic GeoSchem code. It doesn't actually involve any modifications from the same GeoSchem code that powers the GeoSchem Classic CTM or the GCHP CTM, or indeed the GeoSchem code, which is within NASA's GEOS model. The only differences are that there's a new interface which allows it to interface with CESM. This also allows it to present the information that is needed to the modal aerosol model 4, MAM4, in order to generate modal aerosols which CESM can interpret. This is fully coupled. We can run online, although the simulations I'll show you in a second are not. And this uses anthropogenic emissions through the HEMCO module. HEMCO is essentially a grid-independent emissions handler, which through this grant is now available for both GeoSchem and CESM and ChemChem and CESM. This is also, we think, a step towards the grander goals of the Musica project as outlined by Pfister et al. In 2020. I suspect I don't really need to introduce Musica to this community, but the general idea being that we create a modular approach to chemistry for integration into any atmospheric model. Through this project, we are eventually hoping to have not just GeoSchem monolithically available in CESM as a capability, but actually something where we can mix and match different GeoSchem and ChemChem, potentially, I suppose, WACA modules, and see what effect they have in concert and independently. So as a basic evaluation, we wanted to ask how these models compare when simulating, say, 2016 and comparing to observations. So in the slides that are coming up, you'll see results from GeoSchem chemistry embedded in CESM, I'm calling that CGC, ChemChem chemistry embedded in CESM, C/C/CC, and then GeoSchem standalone in its own CTM, S-GC. In this case, they are all using mostly harmonized emissions, something I'll come to later, and MERA2 meteorology. In the case of standalone GeoSchem, this is running as a CTM. In the case of both of the CESM simulations, this is nudged meteorology. So if we look at, say, zonal mean ozone here, this is the simulated zonal mean ozone for 2016 from CESM GeoSchem. It looks plausible. But if we compare it to what we get in, say, CESM ChemChem, we know that we have this low bias that we might have expected. In this plot, blue means that CESM GeoSchem is estimating less ozone than CESM ChemChem. And this is most likely related to the bromine chemistry in GeoSchem, and in particular, the additional bromine emissions through sea salt, which is something that's now being addressed in more recent versions of GeoSchem and CESM GC. However, what was most interesting to us was then the comparison to standalone GeoSchem, where we find that, as we expected, that underestimate in the Northern Hemisphere was largely gone, but we still get a strong underestimate in the Southern Hemisphere. Now, this is most likely due to greater sea salt emissions when we calculate them through CESM, rather through CAM, than when we're calculating them in standalone GeoSchem. However, we also saw this increase in ozone near the tropopause, which we think may be due to differences in water vapor. And that actually brought us to something which was perhaps not a surprise to those of us that use GCMs more frequently, but was a bit of a surprise to some of the GeoSchem community, which is the idea that some of the reason that we're getting a difference between CESM ChemChem and GeoSchem standalone is more because of a difference of interpretation of the meteorology than it is because of necessarily chemistry. So in this case, we know that the nudged GeoSchem and CESM and the nudged ChemChem and CESM are using identical surface water flux, temperature, winds, and surface pressure for MERA2, but then using CAM's physics to diagnose other meteorological variables. And that's resulting in differences in terms of things such as the water field between GeoSchem standalone and GeoSchem when it's running in CESM. And you can see that in the central plot here. We have more water vapor in the upper troposphere when running GeoSchem in CESM than we do in standalone, where it's being read in from MERA2, and then less in the lower troposphere. Whereas when we compare the CESM GeoSchem to CESM CamChem, we don't really have such differences. And this also manifests in differences in cloudiness. Say CESM GeoSchem has almost twice as much cloud fraction, but roughly 2/3 as much cloud water and cloud ice. And this is going to result in differences in the simulation that are more reflective of differences in interpretation in meteorology than any differences in chemistry. And this manifests when we look at, say, the surface ozone concentrations. Now, this plot is a little bit involved, but the x-axis on each plot is the observed concentration at a site annually averaged from 2016. The y-axis is the simulated concentration at a site. And then the three different plots from top to bottom are different regions of the world, and from left to right, CESM GeoSchem, standalone GeoSchem, and CESM CamChem. Now, GeoSchem in CESM is biased lower than standalone GeoSchem and CESM CamChem, likely due to those excess bromine emissions from sea salt that I mentioned earlier. But what was interesting to us was that the vertical spread, so the spread in ozone concentrations at the surface, is more closely related between CESM GeoSchem and CESM CamChem than it is between, say, CESM GeoSchem and standalone GeoSchem, looking in particular at Southeast Asia. And this indicates to us a role of non-chemistry factors, which we need to take seriously, at least in the GeoSchem community, when we try and interpret why we have these differences between CamChem and GeoSchem, and which might then give us some evidence for thinking about how we might be able to improve the simulation in both models. I'll finish it up here. I tried to be short with this talk just by saying that we are starting to understand as a result of this work some of the differences that we see between CamChem and GeoSchem, and hopefully we can use this to further advance both models. The paper that describes this advance is now in GEMDD, and you can get to it through that QR code in the top right, and talks in more detail about how we dealt with aerosols, with halogens, with washout, and so on. And we're very pleased to say that as a result of this work, fully coupled runs and indeed nudged runs are possible with GeoSchem through CESM. And we're looking forward to continuing to work on this to implement it as a standard option in CESM rather than a boutique one, and to continue the modularization of GeoSchem within CESM as part of the musical project. Thank you for your time.
All right, thank you, Sebastian, and the rest of the speakers in this session. There were several questions in the chat. For Sudha, I think they have all been addressed. If I'm wrong, please speak up. And I think the rest of the questions for Raphael, I believe, have also been addressed. Are there any other questions that anyone has for any of the speakers?
Yes, I have a question for Sebastian. In your comparison to CSM, you may want to contact Rafa and compare your version to his VSL version, so then both have the sea salt contributions. So it'd be a more consistent comparison.
Fully agreed. I think the sea salt comparison is one that we've become increasingly interested in, especially because in the latest version of GeoSchem, version 14, we're actually seeing that we have to turn off, say, debromination of sea salt because it's becoming such an important component of how we treat ozone in the model. So getting a better understanding between the different models of how sea salt is treated is I think, actually a very high importance to us.
Okay, yeah. Thank you.
And then I
agree with you, Sebastian. The bromine recycling and the chlorine recycling can really explode in the model. I mean, it can make a really huge source if with the very small changes on the sea salt distribution.
And Julio, you had your hand up first, I think.
Yeah, I had a question for Sudha and Bill. Your results seem to suggest that gravity waves or some other sort of momentum flux carrying things are quite a bit bigger in the stratosphere of MPAS than they are in the other two dicores. And I'm just wondering if you guys have looked at energy spectra of the divergent modes in these three dicores and whether they're different all the way, all the way through, or do they start off about the same and decrease less in impasse? I mean, I'm just wondering if it's a difference in the, damping of the dicore, or whether it's a difference in the amplitude of the source at fronts, or other, other possible gravity wave sources.
So we will have to look deeper into really seeing what's happening there with the spectral analysis, but there is definitely a difference in the damping. And Bill, you might want to explain a little bit about that if you'd like.
Sure. Yeah, we're definitely running less filtering in terms of the horizontal background filters and the upper level damping that, for example, the SE core is using. And I think that may be the primary difference. And plus we're on a C grid, so we don't have to damp as much because we don't have a null space in our pressure gradient divergence operator. So we think that's it, but that's speculation, and we've got to do some more testing and analysis to pin that down.
Thanks. Look really good.
Simone, did you have a question? Your hand was up.
Yeah, I was just on the sea salt again, but I think we should follow up. I just think that the connection between sea salt and then obviously the halogens is very tight, and that is when the sea salt is changing with model versions, it's a problem. And I will talk about it in our timeline. We do implement the new MEM5 version, or we want to, at least we started testing that will change again emissions and burden of sea salt and dust, because it reverts the mode width from the coarse mode of sea salt and dust back to what we had in CSM1. And so it's likely that will change something. And other things are that we are testing some reordering basically of when emissions are taking place in the model and the diffusion that got changed with the implementation of CLUT. And so those things may change again the sea salt, which then may again impact your work. So it may be important to see how scale aware implementations are if things like that change.
Just a comment on this also, Simone, is we haven't really finished our comparison for different vertical resolutions. That's the first thing, without changing into a new version or new diffusion scheme, but at least using the same one, trying to understand the response of the model due to different vertical resolutions will be important also for us, and we are actually working on that.
All right, we have a couple minutes if anyone has any other questions. If not, I do have a question for Tao. You mentioned adding, some sort of additional wave source in a mesosphere, I think, to get secondary waves. Do you have idea of how that would work in sort of practice?
Yeah, there are actually there are two ways. The one is the Hanley discussed with me. The once the wave is breaking, and we add the molecular damping terms. No, the wave is is upward propagating, and once it's breaking, and we only consider the molecular damping, and we set a new wave spectrums, and we consider the molecular damping term effect. And that's more closer to the second wave theory. And or we can set, we just set a damping molecular damping effects above set a new spectrums above the 120 kilometers. Yeah, we just set a new spectrum, a broader spectrum above the 120 kilometers to consider the molecular damping effects, and below in the lower and mid atmosphere we consider the molecular damping. So that's the two ways, and I think the first way is the more reasonable, more physical. Yeah, but yeah, working on it.
All right, thanks. Since I don't see any other questions or comments, I think we can conclude this session here, and we will have 15-minute break, and so we will restart again at 10:40 Mountain Time.
Okay, so we are right on time. Are we?
Yeah, so good. Is Nick still sharing? Who's sharing the slides?
I am not.
Oh, Elizabeth.
I think it might be Elizabeth.
Yeah, yeah. So yeah, we should continue.
Okay. So we will start the third session of science and model evaluation. So as with the first two sessions we have before the break, we will go through these 10-minute talks, and then please include all your questions in the chat, or keep it in mind for the joint questions and answer discussions at the end. So the first one will be presented by Ozone Joe, improvement of secondary organic aerosol representations in ChemChem to match radiation fields in full chemistry version. Go ahead, please.
Yeah, can you see my screen?
Yes, perfectly, and I can hear you.
Thanks. Yeah, my name is Dusong Enkar Akon. So thank you for giving me the opportunity to share some results today. I'm going to talk about secondary organic aerosol parameterization in chem and suggest a new parameterization for consistent radiation fields between chem and chem-chem. Before moving on to the SOA scheme in CSM, I'd like to emphasize why accurate SOA modeling is important based on observation. Here, pie charts are showing globally measured aerosol compositions. Organic aerosols, which are shown in green color, contribute to a significant fraction of submicron aerosols globally. And here's another pie chart now showing further classifications of organic aerosols into primary and secondary organic aerosols. Secondary organic aerosol, which is shown in purple color here, is much more abundant than primary organic aerosol in gray color. Organic aerosol is also important in terms of radiation balance and so climate modeling, because organic aerosols scatter sunlight efficiently as its radius is small. This plot shows aerosol optical depths on the left column and the direct radiative effect on the right column for different types of aerosols. You can see that organic aerosol here on the upper right panel shows the clear signal for radiative effect. So let's look at the SOA scheme in chem and chem-chem. Chem-chem used the detailed chemistry for SOA based on volatility basis set approach with recent findings from chamber and field studies. I'm not going to give every detail in the interest of time here, but basically chem-chem used 10 tracers with 5 for gas and the other 5 for aerosol phase. In addition to number of tracers, here are some discrepancies like online versus offline biogenic emissions and precursor gases and loss processes. These different SOA schemes result in different aerosols between chem and chem-chem. Not only SOA, but also primary organic matter and black carbon through aerosol microphysics in CSM. As you know, the community using chem is a lot larger than the chem-chem community. For example, when I looked at the number of participants in those mailing lists here, I found that chemistry group has a smaller number of members compared to others. This is in part because chem-chem is expensive, so for climate modeling that often simulates more than 100 years, computationally efficient chem model is generally used in many aerosol-related studies. To improve SOA in chem without adding much computational cost, we developed a new SOA scheme for use in chem. There are several updates in emissions, chemistry, and other aerosol-related parameters, but briefly, we added a tracer called SOAE here to efficiently represent the chemistry of precursor gases in ChemChem. And we tried to match model parameters between ChemChem and Chem, but the new scheme doesn't add number of SOA tracers simulated in the model. As a result, the computational cost only adds 2%. And this 2% increase is actually within internal model variability. This slide shows the model result, global atmospheric SOA burden on the left, and vertical profiles of SOA and POM, primary organic matter, using one-year nudged simulation. ChemChem is shown in black, and Chem default is shown in blue. And you can see some discrepancies, such as seasonal variations and vertical profiles in the upper atmosphere, and slight differences in primary organic matter concentrations. The new SOA scheme, which is shown in green color here, reproduce better seasonalities as well as absolute magnitudes. Vertical profiles also better, and also primary organic matter gets much closer to ChemChem aerosol fields. This slide shows annual mean SOA concentrations at the surface simulated by ChemChem, Chem, and Chem with the new SOA parameterization. And differences between Chem and ChemChem are shown in bottom panel. Both default and new SOA schemes show some differences at the surface, especially over source regions. Actually, the advantage of using the new SOA scheme is not apparent here at the surface, but for high altitudes, for example, same plot, but for 500 hectopascal region, default Chem fails to capture the high concentrations over South America and Africa. And this plot is for 100 hectopascal. Again, the new SOA scheme shows similar spatial distributions of SOA, while the default Chem shows relatively constant values. And around 50 hectopascal, the default Chem simulated a way higher SOA concentrations compared to ChemChem, but the new scheme shows generally good agreements compared to ChemChem. So a new scheme does improve the SOA in the model. And actually, until this point, I showed you nudged model run for a year. So now I would like to show you historical runs, 10 years each for 1850s and 2000, especially for radiation fields as well as aerosols. Here, bar graphs show annual mean global burden of SOA, black carbon, and POM. ChemChem shown in black again, Chem in blue, and new SOA scheme in Chem shown in green. The new scheme shows better agreements compared to ChemChem. Especially improvement of black carbon is important, I think, because black carbon is important for absorbing sunlight in the model. Radiation balance is also important, especially for climate research applications. Here I show you net shortwave and long wave at the top of model from ChemChem, and differences between Chem and ChemChem for the default and new SOA scheme. Global mean value of difference is shown in parentheses. Because organic aerosol sunlight, so this shortwave forcing is changed, and differences between Chem and ChemChem are decreased in the new SOA scheme, especially over the polar region here. This slide is for 1850s. And for 2000 simulations, again, the new scheme shows better agreements. But for long wave Pershing, the global mean value gets worse. But this is because the default CAM shows some strong negative bias and also strong positive bias over some regions. So biases are canceled out in the default CAM. This is a summary slide showing bar graphs for global average net shortwave, long wave, and shortwave cloud Pershing and long wave cloud Pershing. Again, following the improvement of aerosols, radiation fields are also improved, especially for shortwave. And furthermore, in terms of differences such as residual energy balance, which is shortwave minus long wave Pershing, CAM with the new SOA scheme shows a less bias compared to CAM-CAM. And for radiate Pershing, so which is shortwave on the left and long wave on the right, so which is the difference between 2000 and 1850s. Again, CAM with the new SOA scheme shows better agreement with CAM-CAM here for both shortwave and long wave. So in summary, organic aerosols represent a significant fraction of aerosols in the atmosphere and also are important for Earth's radiation balance. And CAM used the simplified SOA scheme for computational efficiency, which results in discrepancies in aerosols and also radiation fields between CAM and CAM-CAM. And I think this is a big problem when it comes to climate studies, as most climate modeling studies use CAM instead of CAM-CAM because of computational cost. So we developed a new simplified SOA scheme, and it shows much better agreement in terms of aerosols and also radiation fields between CAM and CAM-CAM, while not adding much computational cost. Okay, that's all I have today. Thank you for your attention, and I'm happy to take any questions in the chat or later in this session.
Thank you, Ozone, and for your nice presentation. We can get the questions later. Next talk, if you want to share your screen, is from Ben Gobert, and it's titled 2 Decades of Carbon Monoxide from Space and Surface in Situ Global Networks and Evaluation of CAM-CAM Simulations. We can see your screen. It's not in full screen mode yet. You can go ahead.
Hi. Yeah, thanks. Full screen now, I guess.
Yep, great.
All right, I'm going to present an evaluation of CAM-CAM with MOPIT data to look at 2 decades of CO from satellite measurements. So yeah, MOPIT has been launched in 1999 and has been providing consistent, reliable results since 2001. And it's consistent with also other infrared measurements from other satellites that have been launched later, as shown here. And the CO column average show pretty marked seasonal cycle, but one of in the northern hemisphere, and different seasonal cycle in the southern hemisphere due to biomass burning. And long-term trends that show overall decrease over the last 20 years, but also before if you look at surface data. But that decline has been slower in the second half of the 2000s. Now there's been a release recently of the V9 version of the retrievals of MOPIT. It includes improvement in the retrieval coverage over polluted areas because of retrievals in high aerosol region. And there has been some significant revision to the NIR calibration scheme, which should improve the temporal consistency of the NIR product and therefore the multispectral product. And so this makes this product particularly good for trend studies and to look at a variation of pollution over time. So here I'm showing 20 years from 2002 to 2021. So actually 19 years, starting January 1, 2002 of MOPIT, dry air column average VMR. And I'm using the monthly mean level 3 product at 1 by 1 degree. So I can plot and apply the averaging kernels to CAM-CAM for the monthly mean as well. And for CAM-CAM, I'm using Anthropogenic the CAMS emissions and QFED for biomass burning, and MERA2 to adjust for the methodology. And I'm doing another simulation with repeated emissions to account for, to estimate the natural variability in CO. And so as usual, if you compare the MOPIT and the model, you see a large underestimation of CO in the northern hemisphere. So the background CO, that can be actually pretty high, larger than 50% of the MOPIT column. And this is a known feature that has been seen in many models, especially global models. This is due to the coarse grid likely and the lack of vertical resolution, and because that makes OH to be too high. But we want trying to go beyond this type of typical comparison. And in particular, over the last 20 years, there have been a large change in anthropogenic emissions with decrease over the industrialized region and increase over the tropics. So this is the difference according to CAMS for January between 2020 and 2002. And you can see actually quite significant increase in regions that are high CO emission, that contains high CO emissions. So when you ask the question, it's like, can we look at the change in trend, seasonal and internal variation, and that what can we learn from those changes to evaluate the model further? And in particular, can we see these in this changing in emissions in the MOPIT record? So here I'm showing the MOPIT total column over the Indo-Gangetic plain, so over northern India. And so I'm applying the STL to decompose the time series into a trend component, seasonal component, and the remainder. So the trend you can see is pretty much the background around 100 ppb, and it's slow variation over time. So the trend represents the changing background over time. The seasonal cycle, around 10% of the CO, and large interannual variability from what remains. So for instance, the 2015 El Nino. Then I'm applying the STL to every 1 degree zonally average MOPIT, as shown here. So you can see the change in background, the seasonal component, and the IAV for every latitudinal band. And so you can see again the decrease of the background over time, and very marked seasonal cycle due to chemistry and photochemistry, and large interannual variability over the tropics due to fires. And again, for instance, 2015 El Nino has a very large signaling of interannual variability. So I did average over large latitudinal band, northern hemisphere extratropics, northern hemisphere tropics, southern hemisphere tropics, and southern hemisphere extratropics. So this is the trend component of the MOPIT data. And I'm showing also the model results here. So again, the background is not very well represented. You can also see the underestimation, but also the variation over time is not very good. And actually the model has more CO in the tropics. But if you repeat emissions, you can see that the increase in CO is due to natural variability from the model. So if we look at the seasonal cycle, I calculated the seasonal amplitude for every year and look at that change in seasonal amplitude over time. And so here are the results for MOPIT. You can see that the actual larger seasonal amplitude occurs in the tropics of the southern hemisphere, and they have been decreasing over time by quite a lot. And it's decreasing also in other regions, while over the northern hemisphere tropics is increasing slowly, or it's fairly stable. If you contrast here for the seasonal cycle, the models are doing a better job in terms of absolute values, although in the beginning of the record is underestimating the seasonal amplitude for the tropics southern hemisphere region. And the model show a decrease in seasonal amplitude for in the tropics, while MOPIT doesn't show that in the northern hemisphere. But you can see that this change of seasonal amplitude are due to emissions, because the repeated emissions doesn't show that. We can go further and look and focus on that change in the tropical southern hemisphere region, and looking at the monthly data and seasonal amplitude time series using CO tags. So here it's just a model. You can see that the peak of CO, of the maximum CO, is due to biomass burning, and that the emissions are decreasing over time. So they are responsible for the decrease in the peak of the seasonal cycle, and therefore the seasonal amplitude. If you repeat emissions, there would have been a slight increase. We can also look at other variables, such as like methane, CO from methane that is also tagged, the chemical production, chemical loss. And there is a strong dependence, a strong correlation between CO from biomass burning to the CO column. To look at regional scale, I'm taking the example of Northern India again. The trend component of MOPIT is fairly, doesn't change much over time, but there is kind of a reversal in the sign that is due to emissions according to the model. If you want to look a bit more into details, I removed the trend component, and then you can see that the signal of increasing anthropogenic emissions in the region is much more clear, although everything is on the same scale here, so it's harder to see. And we can also look at the CO tags to quantify those changes, and it's also suggesting that this is due to the change in anthropogenic emissions over time. I'm going to stop here, and I'm happy to take any questions.
Thank you, Ben, for your talk. We will move to the following one and last of this short session. Jungpian Su, if you want to share your screen, the presentation title is Hungatong Eruption, Stratospheric Aerosol Evolution into a Water-Rich Plume. Go ahead, we can see your full screen.
Thank you. Hello, everyone. I will talk about our CESM2 MEM simulation of the Hungatonga eruption. First, I want to thank all my co-authors, especially NCAR team are so supportive, and many of the people at NCAR involved in this work. So if you are interested in this work, we have a preprint now and online, and you can read for more details. So I will start with the story of the water and aerosol evolution from the CSM model simulation. For the Hungatonga eruption, it injected a moderate amount of SO2 and a large amount of H2O into the stratosphere. So those water, some of them stay in the water vapor phase, and some of them form ice. The water vapor provide a very abundant OH to react with SO2 that create the H2SO4 gas through the nucleation, coagulation. It formed the sulfate aerosol in the stratosphere. Because of the abundant water vapor, those sulfate aerosols swollen to larger sizes. So there are a couple of interesting science questions we are addressing in this work. So first, how much water injected in ice formed during the initial phase? What does the water vapor mean for the SO2 lifetime? What process controls the aerosol particle size, coagulation, or swelling? So, with very a moderate amount of SO2 injection, how long will this eruption actually affect the climate system? So there's a recent paper by Louis Milland that they says the MLS shows about 150 teragram of water injected, increasing the stratospheric H2O by water vapor by 10%. So we use a model to try to match the MLS observations for the first 3 months. So eventually our injection has 150 teragram of water injected and 20 teragram of ice formed, and eventually 140 teragram of water vapor persists after a week and until also persist more than 3 months. So what we find the difficult part is to limit the ice formation during the initial phase. So this figure shows that the amount of water retained is determined by how much ice formed and determined by the ice vapor pressure curve. You can see that between 20 and 50 millibar, this curve, the water vapor saturated water vapor curve is very sharply changed because of the temperature is changed rapidly at this area. At 20 millibar, which means at 20 millibar, if we inject a big amount of water in there, and about 2000 ppm water can stay in the gas phase. However, if we inject the water into the 30 millibar, it can only hold 500 ppm of water. So this figure, we explore the SO2 burden as a function of time, which indicate the SO2 lifetime after the Tonga eruption. So the symbols are the observations. And firstly, we inject the SO2 into the only, and the model produced a lifetime of 28 days. And then we inject the water, which significantly reduce the SO2 lifetime. This is because the H2O provide significant amount of OH. You can compare to the left panel and the right panel. You can see the left panel, the SO2 deplete the OH, and it takes time to form more OH to react with the SO2. While on the right side, you can see in the plume that we always have abundant OH to react with SO2. So the conclusion is that the water injection significantly shortens the SO2 lifetime by providing abundant OH. This figure is the aerosol optical stratospheric AOD compared between the AMPS and the two model simulations without the water injection in the middle and with water injection in the middle. It's pretty obvious that with the water injection, we get higher optical signals, and we have the sulfate form right away because the shortened SO2 lifetime. So we investigate if this the large. So we find the larger effective rate, larger AOD is because the particle is larger in the when we injected water, and the effective radius of the particle increased by 50%. So we wonder if the swelling or the coagulation of the particle are the reason for this large effective radius. And we find that the particle mass only increased about 50% of this because of the swelling of water. So to conclude this part is that because of the short SO2 lifetime, subsequent coagulation creates larger sulfate particles that double the stratospheric aerosol optical depth. We also run the model with several ensembles to extend the prediction until this summer, this fall, 2022. And we find that the volcanic plume will transport and enhance the aerosol burden and water vapor near the polar vortex until at least October 2022. And especially if you look at the right bottom corner, that the sulfur inside the polar vortex get almost doubled by the end of October here. So we don't see much signals inside the polar vortex from the H2O because inside the polar vortex, it forms polar stratospheric clouds. It created lots of variability in our ensembles. So if we look at the zonal average picture in late September, we can see that the H2O still increased by 2 to 3 ppm from 60 south to the tropical region, and the SAD it increased inside the polar vortex around 100 millibar, and also the majority increase is in the mid-latitude. So here's give some numbers of the background water and the background surface area density. You can see those numbers are pretty significant still in September. So here we think those increasing may impact the heterogeneous chemistry because, for example, the reaction probability of ClO2 plus HCl will increase by 1 order of magnitude if we increase the water by 3 ppm. So here's my conclusions. I will leave it here and end my talk. Thank you.
Thank you very much for your presentation. We can now get into the questions and answers of the different talks. If you could please stop sharing your screen. Thank you. There have been some questions already on the chat that most of them I think have been answered. Someone else has a question, want to open the microphone or just raise your hand. Ben, I was just asking you on the CO variability and the chemical sink. Do you have an estimate of how large this sink by OH is, and if this the OH has a large seasonality, and if that's impact on the model or on the observations from output?
Yeah, it does. It's very important, but we don't have much constraint about what should be the real OH. So in the past studies, the high CO in the winter was thought to be due to lack of emissions. But if you use the Transcom OH derived from methyl chloroform, that suggests no interhemispheric gradients, so you would have less OH in the northern hemisphere. If you use that, then you would have much more CO in the winter. And so typically when you have NOx emissions in 1 degree grids, you end up with too much OH in the winter that is responsible for that bias. I think otherwise OH is pretty well represented in the model. Just maybe slightly overestimated.
Okay. Okay, thank you.
Rafa, I have a question for Wenchen.
Yeah, go ahead.
So you showed a figure in I think it was latitude versus time in a given pressure altitude. And it looked like that the model wasn't spreading SO2 or whatever as much as the observations were showing, or maybe it was water vapor. Do you want to comment on that? Do you have any idea why the model doesn't want to spread latitudinally more than observation?
Yes. Yeah. So this is one thing that we keep discussing. So first, we try to just inject in a larger area, so we don't have we have wider spreading, but the spreading still cannot spread as large as observation. And one particularly problem is spreading across the tropics is because like the modeled meridional wind is really small, and I think in reality there's wind shears that more mesoscale maybe get push the plume faster meridionally. Also, it could be the plume itself has a different temperature than the surroundings, and has some plume dynamics that make the plume spreading faster. So we probably would like some help from other people if other ones have ideas. Yeah, thanks.
Thank you.
Okay, so there is a question from Susan on the chat. How are the lower boundary conditions for greenhouse gases determining WACOM, and are they compared with observations similar to the CO carbon monoxide study? I don't know if this is more for Ben related to the CO, or for you, Jung-Han.
I think it can play a role, but overall the CO from methane is not that important. It would impact the background in the tropics. But yeah, that's something I'm interested in, and I think it would be interesting to run with methane emissions in the future. I think the lower boundary conditions are made by DOG based on CMIP6 protocol, which is monthly latitudinally averaged. So based on observations until 2014. So I think for the WACAM and CAMCAM, they're CMIP6 scenarios right now.
Okay, any further questions for this session? If not, we are right on time to start the last session for the future plans and discussion. I pass it back to Nick first.
All right, can y'all see that?
Yep.
Okay, great. I'll just keep it in this non-presentation mode. So yeah, our hope with this discussion session is to rehash some of our development timelines and the sort of strategies and goals we have for the remaining life of CSM2, the CSM 2.x release, and then CSM 3. So we'll just represent the whole atmosphere timeline first, and then I'll hand it over to Simone and Rafa for the chemistry climate timeline. And so I think actually you've seen quite a few talks today on some of the things on the left-hand side of this timeline related to them. So we've had some discussion of updated chemistry and physics and some improved and new dye core support. So again, we're in mid-2022. So we have here initialized prediction comp sets, which was sort of a, I'll say right now, pie in the sky, but I think we're pushing to get this done because it has a lot of, I think, ability to support community projects. It's a good follow on for our existing Earth system prediction real-time forecasts. And then moving forward again, things like TM and transport diagnostics being an online available output, so folks don't have to save high time resolution output to look at dynamics and transport. Let's see if I can get there we go. Hold on. Okay. And then updating the SD model, or the SD approach. So we've had a few studies published recently and about the last year, talking about some of the current deficiencies with that and how we can improve it. There are a lot of physics updates coming on, including things like KARMA, working towards scale-aware gravity wave schemes here down the line, which is important not just for regionally refined simulations like folks have been showing, but even some of our meshes like the cube sphere mesh have quite a variation in the grid size over just the uniform resolution mesh. And so we want to make sure we're treating everything properly. Then finally, we've shown the future vertical grid for the WACAM integration with the L93 workhorse model. And we're thinking of two options for how to handle that, whether we stack WACAM on top or whether we transition in the stratosphere to a just generally higher resolution WACAM.
Thank you. Can you reload? I changed something. Nick.
Re-screen share, you mean?
Yeah.
Okay. All right. 1 second. I will try that again. Okay, you see that?
Yeah, well, it doesn't matter. Okay, I'll just say I did add or change something. So this one is more separated between developments. So this is basically the first slide is more like developments towards this winter and fall and not summer 2023. And then the next one is more longer term developments. It's still hopefully going towards Chem 7. We're not talking really about CSM 3 at this point. So that's what I removed. So please disregard that at the title. Yeah, so for our we already had a talk today on the new SOA scheme. So what we'll try to do is get into new chem, some new features that will in particular be important for chem that are relevant, of course, that are aerosol relevant changes and chemistry relevant changes for simple chemistry. And things like DMS emissions already in the development code. A new dust team is currently developed. But what I also pointed out earlier is the MAM5 scheme, which is both important, not only for chem. I mean, it's actually designed for WCAM to have a coarse mode sulfate aerosol, but it's also important because we're changing the sigma ranges back to what it was to CSM1, as I mentioned before, which is something we think it needs to be added quickly. So whenever tuning is happening in Chem 7 and WCAM and other models, we have that already integrated, as well as the discussion of marine organic aerosols that possibly change the radiative forcing. But then for chemistry on point 2, we do have new developments coming in. I mean, there is updates on the chemical mechanism and the photolysis lookup table, but eventually, and hopefully by the end of the year, we do work on the new photolysis scheme, which we call TOVX. And that will be eventually coupled to CESM, hopefully sooner than later, that it can be integrated and will be allowing much more great science that already people do in other versions of the model. We heard about VSL chemistry today, and we added already upper boundary conditions for the L58 model. And we also heard about the emission tool HEMCO today. So what I want to discuss, and it would be great if we have a little discussion on the concepts that the community would desire for the new developments. And in particular, when you talk about the workhorse model, you know, what do we need also in terms of horizontal resolution? We go up in vertical resolution, but in some places, you know, a 2-degree model is still valid for some research. And is that something what we want to move forward and test? The more concepts, the more, of course, work and support is needed. But that's something I think is important. And the second slide, please, Nick, to the next slide. Yeah, and so that's more hopefully by next summer. So we talked about the flexible aerosol interface in my overview talk. And while we are developing the aerosol schemes like Karma and others, we think we will merge that over into the development version with this new aerosol interface. And that will allow other capabilities also, and hopefully easier integration, like the brown carbon that is in a sandbox for a while, as well as other things. So this is, well, we'll see how fast the development goes, but hopefully moving forward further along. And then also chemistry updates. And here, what I added in a new slide was actually what Ben just said. How much do we also want to focus on methane emissions? You know, we had that great overview talk on Monday on also the needs for methane emissions and also other chemistry. And finally, what we really need is community support. We have seen the great work together with the Harvard group here with the HEMCO emission data set on Chem 7 and also GeoSChem. And then other things that are worked on in the community, and some are missing here. For example, yeah, things like NOx emissions, or also land and megan developments that should be added here. And finally, we're working on melodies. So that's all ongoing and more planned towards next year, summer. That's it. And now I think what we want is, I don't know if we want to continue sharing or if we just stop sharing and have a discussion. Nick, go ahead.
We can always bring it up if someone has questions. I guess what we can say is, maybe it'd be good to just bring it back to big picture. Whole atmosphere side, we're very concerned about vertical levels of the new workhorse configuration, but for a lot of you using not the workhorse configuration of the model, you're probably interested in the improved physics coming online and some of these scheme changes. But from our perspective, we really want to know, is there anything egregious we're missing? Are we making progress? I don't know if you want to say anything about CCWG or not, but if there's a few big picture things.
Yeah, you can write your thoughts in the chat again, or you can just raise your hand. Any comments are really helpful, as Nick said, on webcam, vertical grid, on what do you want to see happening, also priorities, what we presented as priorities. Do you see anything that really you think we should push forward that really needs to go in the model? Yeah, we'll try to do our best, but it really is important to get the information from the community on here as well. Is there anything also this is combined with WebMX, so I don't know if there is anything in that regard as well. It seems like everybody likes what we are doing. Doug, good. Yep.
Yeah. So, there's one maybe development process or a project we haven't really addressed, is that we've kind of had a situation set up in the past where we have heterogeneous chemistry in the stratosphere, we have heterogeneous chemistry in the troposphere, and there's really no reason why we can't make that more of a universal, from the surface up to through the stratosphere. And so I think that's an effort that we might want to add to the list to kind of figure out and update before we, by the end of the year, something like that.
Mike, do you want to comment?
Just that part of that is a different treatment of aerosols and the sulfates, and the way MAM was designed was to treat tropospheric aerosols. So sulfates are treated as involatile solid ammonium sulfate particles, and then when we added the stratospheric sulfates, we magically turned them into liquids above the tropopause. And the correct way to do that really is to keep track of ammonium in the aerosol, which I think MAM 7 does, right?
Well, we also have this mosaic scheme that does actually keep track of, and Dusong has worked on that version quite a bit, and Xiaohong's group has initially worked on this. But so I think that's really a good point. Part of the interface of the aerosol interface will make the integration of mosaic helpful. Then we do have nitrates, and I think that could be the next step, really, to say, let's also try to get rid of this disconnect or this difference between the stratosphere and the troposphere, because that's if it's really ammonia dependent, I think we'll first have to have mosaic included in the model. Other comments that oh yeah, Susan, please go ahead.
Thank you so much for the session. I have, I'm kind of a little bit newer to the modeling, so I just have a background question, I guess, which is, I think today you were mentioning that the chemistry models, that there are different kinds of chemistry models that are run depending on the situation, because some of the chemistry models take so much computing power. So I just was wondering for Wacom X and Wacom, are the chemistry models that are run in the troposphere, do they include lower boundaries that have, this is a follow-up question, but that have geographic dependence or regional dependence in terms of the lower boundary sources for the greenhouse gases? Thank you so much.
In general, the boundary conditions at the surface are taken from assessments like CMIP6, and they typically have a latitudinal dependence and a seasonal dependence, but they're not. There's no longitudinal component to it. There's no mean.
Right. For the long-term the long-lived greenhouse gases, short-lived things like SO2 pollution has regional, latitudinal, longitudinal dependence.
Yep.
And what about methane? Methane, is that considered a shorter term or longer term?
It's probably it probably just has a zonal mean, but I'd have to check that.
It does. It's a mole fraction boundary condition, but it doesn't have to be. I mean, we could switch to an emission-based boundary condition if the data set's available.
Okay. Oh.
Yeah. Currently, on the Lee et al. Paper that I presented the results of the chlorine impact on methane, we use an emission inventory for methane with a spatial resolution.
Well, thank you. And that you said that paper was referenced in your talk? Is that?
Yep.
Okay, I'll take a look for that. Thank you.
Any other questions or thoughts? I do wonder, since I don't know, we have a bunch of people in this working group. How many people would be actually thinking that a support of a 2-degree version, a cheaper version of the workhorse model would be something you'd be interested in? So I think that currently the costs will increase, and we're still figuring out the costs for the 58 and the 93 level model, but some maybe studies like Doug is using often a 2-degree model for quicker studies. When we move to spectral element, I think mostly everything is developed with 1 degree. And I actually wonder if people could raise their hands if they are interested also in the 2-degree study in terms of performance and other things, so science-wise.
I think especially going to a higher vertical resolution in these, we need to keep supporting 2-degree. Like I would say for Wacom, 2-degree and 2-degree MA is something we absolutely can't leave behind, and probably need to develop closely parallel, because otherwise it's just too expensive. I know a lot of folks here have to get allocations and things, but even for people with access to lab accounts and stuff, it's still expensive to run 1 degree. So.
I will also add that we have a 2-degree version of Wacom 6 finite volume where it's 110 levels, and it gives a really nice QBO. And so you can get a QBO at 2 degrees. So we should probably think about working towards that with a spectral element, 2 degree, 93 level or something like that. Whatever Nick decides the vertical gradient is going to be, vertical width of the model.
Yeah, from the university and also several of people from university I know about, it's just too expensive for us to run a 1 degree model and using our own resource or using the NCAR resource that we apply for. So most of us usually just go with 2 degree first, and then maybe 1 round degree when all our test is more complete, and just running 1 degree is taking a long time and also too expensive for us to afford.
And it's very important for the paleo group, which does 1,000-year runs or longer.
Yeah, and what I wonder when we see these really nice Musica version 0 runs, when we are interested in the local air quality, regional air quality, that doesn't matter anymore then, because you really spend most of the time probably on that regional refined grid and just save a little bit. So I think that's why most of the people that are looking at Musica are probably don't need that. But yeah, it seems to be for more, like also for the karma configurations, more the stratospheric applications important in the long term. Okay, that's good to know. Maybe, I don't know, do we have other questions? Dusan, go ahead.
Yeah, I think the other day we were talking about CESM version of the spectral element grid. So with CESM for CAM, I think I heard that computationally using CESM is cheaper than the default spectral element grid. So just wondering about how things goes with this CESM version.
I don't think it improves much at this point. I did 2 test simulations with the 93 level and with chemistry, and it was still pretty expensive. I think Peter is on here, Lauritsen. I saw him somewhere to comment on that.
Yeah, I'm here.
Hi.
So we haven't really optimized spectral elements with CSLAM for Wacom yet. We're having instability issues. So right now we're running lower time steps than what should be possible from theory. So I hope that once Nick has the new grid ready, that we can start fine-tune these things. But right now I think we're using like 2 or 3x shorter time steps for the vertical remapping that we would like to. So I hope we have room for improvement right there. My suspicion is that it's the gravity wave scheme that makes the model go unstable. So it deposits huge amount of momentum, and since the SE core has less diffusion at the grid scale, it tends to make the model unstable. So it would be nice to explore. I have some ideas we might explore to try and get around this, so we can actually run with longer time steps to get the benefit of CSLAM advection.
And I assume that you're talking about the 93 level version. Would that be also applying to the workhorse model that is basically the low top 58 level version?
Well, when you have a model top at 80 kilometers, we're not having any stability issues and we're running with optimal time steps. That's what's happening in CAM right now. But we're getting similar throughput as FV with moderate call counts. And we can scale it out to get more throughput than FV. But when the top is above 80 kilometers, the vertically breaking gravity waves really grow large, and it's been a challenge to stabilize. And that's what I want to explore with Nick once he's ready. So the 80 kilometer top, I'm pretty happy with the time stepping, but I'm very unhappy with the Wacom SE time stepping right now.
Yeah, I think we have issues with adding chemistry, which adds huge, it doesn't scale the same as we expected. And I think we need to have more discussion on that as well.
Yeah, so as soon as the time step is restricted for the transport, then adding more tracers will make performance even worse.
Yeah, I think online meetings are tiring and the discussions are just not the same as when we're sitting all in one place. Hoping to be back at one point in person and have better discussions. I think we'll can wait a little longer for people. We can also resume early, I don't know.
I mean, we don't even just have to take questions. If people also have major issues with the model, that's also a good time to say something. I mean, I will just say to reiterate, like a lot of this development is adding computational expense. So I think these lighter weight configurations didn't get the same resources and attention this last cycle, probably because it wasn't so expensive just yet, but for sure going forward, we know this is an issue. Yeah, Peter.
Yeah, I also wanted to add, with respect to the 2-degree configuration, there's also a lot of interest from the paleoclimate community. So I think it'll be a really nice addition to start working on that with spectral elements.
Susan?
Yeah, okay. Yeah, I mean, we discussed that a little bit. Susan, do you have another comment?
Oh, I don't want to take, if somebody else wants to go first, they can go, but otherwise, oh yeah, thank you. I was just wondering, is there any, are there any needs for maybe from the middle upper atmosphere community, research community that can help with some of the tropospheric studies? Like, so if we look at the upper boundary for tropospheric studies, are there any particular, is there particular information that's particularly helpful from the whole atmosphere studies to help with answering questions also relating to the troposphere?
Yeah, I'll just say I think probably the folks doing the Asian summer monsoon work are a pretty good cut of vertical levels. That topic seems to have bridged the two communities, but in regard to anything else, I'm not sure. Seems much less integrated. At least that's my impression. But I know TropeChem folks look at tagged ozone a lot, like O3S. So there's at least some use there of trying to understand strat trope coupling. It's probably an issue of timescale, but I don't know. The folks who do TropeChem maybe can answer that better, what they think they need, or if there's an opportunity. I will say there's probably, so the session tomorrow on Earth system prediction is probably like the dry dynamics version of this community kind of uniting. So there's a lot of folks in that tomorrow that are going to be focused on strat trope coupling and even some stuff higher up, just because the dynamics are a fast mechanism there. But yeah, I guess one issue going forward, and this kind of relates, yeah, I was going to say, I think this relates to this economical configuration need, is stuff like the MA scheme, the middle atmosphere chemistry scheme. So for a lot of longer term geoengineering stuff, there's pressure to use MA because it's 3 times cheaper to run that model than it is to run with the comprehensive chemistry. But obviously that there's some issues because we're neglecting some important tropospheric processes, and like Dan has shown, the strat aerosols tend to be mucked up by not getting the right SO2 oxidation. And so I think there's probably, I don't know if there's any, I am not a chemistry person, but I would say like the MA scheme, I think going forward is really important for a lot of this stuff too that folks have been talking about, including even the paleo community. But it would be good maybe at some point for that scheme to maybe be adjusted in a way that the aerosols in the stratosphere can be a little more accurate. If there's any way to do that without having to add too much chemistry complexity. Simone, I don't know if that's your arena or not, but it's something that Dan and I have been talking about because it would be nice to find a fix.
Yeah, I think there is one thing. Dusong started with one fix. I think there is a difference between tropospheric aerosols just because you are prescribing the chemistry, and what he just showed will benefit the middle atmosphere WECM. It's not only chem. It actually will also make WECM middle atmosphere more similar to WECM. So that's one thing. The second thing is that sulfates are different in the troposphere. You said, yeah, in the middle, in the UTLS, or so there's different oxidation, and that's also for the troposphere. You do have prescribed fields of oxidants, and those simply result in different sulfate, because you don't have the variability. So there are possibilities, and I think here are people from also the HEMCO group and Louisa on, we could include potentially capabilities to impose a seasonal cycle on the oxidants in the troposphere, potentially even where Danielle sees the problems to improve this problem. And I don't know, Louisa, if you want to comment on that.
Yeah, so there are maybe 2 different things. Middle atmosphere chemistry is interactive chemistry. So it's not specified oxidants in the troposphere, but it only has methane as a hydrocarbon in the troposphere. So you're missing all the VOC chemistry. So that may be, that could be an important thing to come up with some simple chemistry to expand on just methane oxidation so that you have better OH and thus better sulfate in the troposphere. That there could be a lot of different viewpoints of what needs to be, what's most important to get right. But if we could get ozone and OH closer to chem when we use middle atmosphere chemistry, that might be a good goal. And I'm not sure we've really compared that at all. So that's one aspect.
Right. But the SOA will be improved with Dusong's new scheme because that's independent, because we're adding a lifetime tracer, I would think. Is that correct? For the middle atmosphere chemistry?
We could we could improve the SOA with the same scheme, but it would be using the calculated OH and ozone oxidants. Yeah, we should look at that. That may be one area of, one simple improvement. But to improve the hydrocarbon CO NOx chemistry, we probably need to add some more something, more VOCs. And another thing I was thinking about was, so I think that should be in, that's certainly something to think about, how to improve the middle atmosphere tropospheric chemistry. Another thing we've been talking about a long time is improving the, or we want to keep adding tropospheric chemistry. And so would there be some way to go back to having a specified stratosphere to reduce the costs, that if we're primarily interested in lower tropospheric chemistry and want to add a lot of VOCs and other things, we could specify stratospheric components somehow. And I know Ben is interested in that, for data, also for data assimilation studies where we don't need to calculate all of the stratospheric chemistry. So that's something else we could look at. And if anyone's interested out there in helping with any of these questions, let me know.
Yeah, just thinking that I forgot that exactly, that we don't prescribe the oxidants in the troposphere for WACM middle atmosphere, but it could be an option, another option. But would that work? Probably not. We do divide between troposphere and stratosphere.
Yeah, that might be worth exploring. That might be a cheap option.
Maybe it's petering out. Maybe we actually are going to be able to end on time. Everyone's vaguely happy with what's going on.
Yeah, send us any emails or thoughts or interests in ongoing stuff. This will be posted, all the talks will be posted, and hopefully we have in-person meetings again. That makes it easier, and yeah, I think more fun as well, eventually. So I think we can, if there are really not any more questions, I would say we can stop recording now and resume or end the session. And then